Okay, hello guys. In this video, what we are going to do is we are going to watch all the videos from Essence of Calculus. And the thing is, like, I actually don't like watching the stuffs alone. Yeah, these math videos, and I like to discuss them with someone who is beside me. Basically, for now, you viewers are beside me, and whenever we are watching, like, I might pause at some moments and share my thoughts in it. Yeah, basically, even if you have thought of watching them, uh, it's really boring to watch it alone sometimes. So that's why we'll watch it together, and at some points I might pause and share my views. Yeah, at some point, like, I might not be able to understand, so like we will take some time to understand those, and we will go together understanding all the details, and those are covered in this series. Okay, so let's begin now. So there are basically 12 videos, and those are around 20 minutes long. So basically we will try to complete all of them, so let's see how much we can. Let's begin with the first video, and I'm really excited because his videos are too cool, and at some points they really give us some beautiful insights. So let's begin. The art of doing maths is finding that special case that contains all the germs of generality.
Hey everyone, Grant here. This is the first video in a series on the essence of calculus, and I'll be publishing the following videos once per day for the next 10 days. The goal here, as the name suggests, is to really get the heart of the subject out in one binge-watchable set. But with a topic that's as broad as calculus, there's a lot of things that can mean. So here's what I have in mind specifically. Calculus has a lot of rules and formulas which are often presented as things to be memorized. Lots of derivative formulas, the product rule, the chain rule, implicit differentiation.
Yeah, I do also agree that like most of them are just rules, and we just need to know rules, and we are able to do everything else without like really understanding those things. Like if we just know product rule or quotient rule or let's say the power rule, then it's real easy to compute all the derivatives without actually knowing what they are. Yeah, so I do agree with them. And yeah, so this was power rule, and let's check them one by one. So power rule
Lots of
and
derivative
product
formulas,
rule. Yeah, f z dash plus z f dash.
the product rule, the chain rule, implicit differentiation.
So is this implicit differentiation? But it seems like it's Leibniz formula. Yeah, basically, what is he doing? Oh, this is basically the derivative. Okay, he is differentiating this from 0 to x, and this is in terms of t dt. So is this implicit differentiation? Mm, I don't understand this right now. Okay, let's go.
The fact that integrals and derivatives are opposite Taylor
Oh
series,
yeah,
just
yeah,
to
but in fact,
differentiate.
like this might be the fact that integrals and derivatives are opposite. So this is this integral, and we are differentiating and again integrating and getting an integral. Okay, integral derivative integral gives the integral. Nice.
The fact that integrals and derivatives are opposite Taylor series, just a lot of things
So
like
Taylor series, you might know this. So basically, this is centered at a, so we have x minus a over here, divided by n factorial, and the nth derivative evaluated at a. We are solving all of this. So this is a really powerful technique. Even if we have to integrate f, we can integrate the sum and integrate part by part, so that makes it easier.
that. And my goal is for you to come away feeling like you could have invented calculus yourself. That is, cover all those core ideas, but in a way that makes clear where they actually come from and what they really mean, using an all-around
So
visual.
yeah, so this means each of the length are increased by dx, and probably uh, what he might want so is f of x plus delta x minus f of x by delta x. So basically x plus delta x whole cube minus x cube by delta x. That means 3x square delta x plus 3x delta x square minus delta x cube by delta x, and we get 3x when delta x goes to 0. Yeah.
Will approach. Inventing math is no joke, and there is a difference between being told why something's true and actually generating it from
Yeah.
scratch.
This
But
is
at
the
all points,
DF.
I want you to think to yourself, if you were an early mathematician pondering these ideas and drawing
This is a product rule, is it? Yeah. For product rule, let's say we want to differentiate the product of f and z. So this one over here is df dz. This one is df dz. Yeah. So basically, this is really negligible. This is so small. That's why the derivative of f times z is just this area, which is df times z, in this area, which is dg times f. So their sum df times z plus dg times f, that can be told as the derivative of a product. Yeah.
out the right diagrams, does it feel reasonable that you could have stumbled across
Yeah.
these truths yourself? In this initial video, I want to show how you might stumble into the core ideas of calculus by thinking very deeply about one specific bit of geometry, the area of a circle. Maybe you know that this is pi times its radius squared, but why? Is there a nice way to think about where this formula comes from?
Yeah, one of them, like, okay, but for that also you need circumference. If we had circumference as 2 pi, then we can break this. But also through integrals, also there are some nice ways. I think you will show those in later videos as well.
Contemplating this problem and leaving yourself open to exploring the interesting thoughts that come about can actually lead you to a glimpse of 3 big ideas in calculus.
Okay, so basically he like broke these into rings and then placed those rings to form a triangle. I think this one is 2 pi r. The height is just radius, so 1 by 2 pi r into r. Yeah.
Integrals, derivatives, and the fact
No, this integral from 0 to r of dA by dr. Okay. So dA by dr is the area of a ring, yeah, and dr. So all the rings times small radius, ring times small radius. So it's basically computing all areas of all the rings with very thin radius from 0 to r. So that gives the area. Yeah.
that they're opposites.
Okay. So integral is capital A times r. Yeah. Fine.
But the story starts more simply. Just you and a circle. Let's say with radius
Let's
3.
begin now.
You're trying to figure out its area, and after going through a lot of paper trying different ways to chop up and rearrange the pieces of that area, many of which might lead to trying different ways to chop up and
the first one
trying to figure
was
out its area. And after
vertical,
going through a lot of paper trying different ways to
horizontal.
chop up and rearrange the pieces
now this one is unique. Like I've never seen it, but like if there's any way to chop this way and find the area, I would be glad to learn that if that's here.
of that area, many of which might lead
This one is also well known because this is just like our del is just angle, and for every angle find the area. Yeah, find the area in terms of del theta. I mean find del area in terms of del theta and then integrate from 0 to pi. Yeah, this one is well
to
known.
their own interesting observations. Maybe you try out the idea of slicing up the circle
Oh yeah, this one is also already discussed. Yeah.
into many concentric rings. This should seem promising because it respects the symmetry of the circle, and math has a tendency to reward you when you respect its symmetry.
Nice.
Let's take one of those rings, which has some inner radius r that's between 0 and 3. If we can find a nice expression for the area of each ring like this one, and if we have a nice way to add them all up, it might lead us to an understanding of the full circle's area.
Yeah.
Maybe you start by imagining straightening out this ring. And you could try thinking through exactly what this new shape is and what its area should be, but for
Trapezoid,
simplicity,
yeah.
let's
It's
just
trapezoid.
approximate it as a
It's actually trapezoid. Yeah. Because like it doesn't really get into rectangle because when it gets straight, like some of the areas of the outer part, the outer length is bigger than the inner length. That's why the outer length should be bigger here.
rectangle. The width of that rectangle is the circumference of the original ring, which is 2 pi times r, right? I mean, that's essentially the definition of pi. And its thickness? Well, that depends.
Okay, so this formula is basically from the definition of pi. Like it's not derived because pi is defined as circumference by diameter, so that's why circumference is pi times diameter. So this is just definition, yeah.
On how finely you chopped up the circle in the first
And
place,
yeah, and
which is
that is
kind of
just
arbitrary.
the dr.
In the spirit of using what will come to be standard calculus notation,
And for it to be rectangle, we need to have
let's
a
call that
very
thickness
small radius.
dr
Yeah,
for
dr.
a tiny difference in the radius from one ring to the next. Maybe you think of it as something like 0.1. So, approximating this unwrapped ring as a thin rectangle, its area is 2 pi times r, the radius,
Yeah, if
times
it's a
dr, the little
rectangle,
thickness.
very thin, then it's
And
2
even
pi
though
dr.
that's not perfect, for smaller and smaller choices of
Yeah.
dr, this is actually going to be a better and better approximation for that area, since the top and the bottom sides of this shape are going to get closer and closer to being exactly the same length.
Yeah.
So let's just move forward with this approximation, keeping in the back of our minds that it's slightly wrong, but it's going to become more accurate for smaller and smaller choices of dr. That is, if we slice up the circle into thinner and thinner rings. So just to sum up where we are, you've broken up the area of the circle into all of these rings,
Yeah.
and you're approximating the area of each one of those as 2 pi times its radius times dr, where the specific value for that inner radius ranges from 0 for the smallest ring up to just under 3 for the biggest ring, spaced out by whatever the thickness is that you choose for dr, something like 0.1. And notice that the spacing between the values here corresponds to the thickness, dr, of
Yeah,
each
yeah.
ring, the difference in radius from one ring to the next. In fact, a nice way to think about the rectangles approximating each ring's
Nice.
area is to fit them all upright side by side along this axis.
And that forms a
Each
triangle.
one has a thickness dr, which is why they fit so snugly right there together, and the height of any one of these rectangles sitting above some specific value of r, like 0.6, is exactly 2 pi times that value. That's the circumference of the corresponding ring that this rectangle approximates. Pictured like this, 2 pi r can actually get kind of tall for the screen. I mean, 2 times pi times 3 is around 19. So let's just throw up a y-axis that's scaled a little differently so that we can actually fit all of these rectangles on the screen. A nice way to think about this setup is to draw the graph of 2 pi r, which is a straight line that has a slope 2 pi.
Nice.
Each of these rectangles extends up to the point where it just barely touches that graph. Again, we're being approximate here. Each of these rectangles only approximates the area of the corresponding ring from the circle. But remember, that approximation, 2 pi r times dr, gets less and less wrong as the size of dr gets smaller and smaller.
Yeah.
And this has a very beautiful meaning when we're looking at the sum of the areas of all those rectangles. For smaller and smaller choices of dr,
Yeah.
you might at first
smaller,
think that
smaller
that
choices,
turns the
like the area is actually equal to the area of triangle itself. Yeah.
problem into a monstrously large sum. I mean, there's many, many rectangles to consider, and the decimal precision of each one of their areas is going to be an absolute nightmare. But notice, all of their areas in aggregate just looks like the area under a graph. And that portion under the graph is just a triangle with a base of 3 and a height that's 2 pi times 3. So its area, 1/2 base times height, works out to be exactly pi times 3 squared. Or if the radius of our original circle
If it's
was
r,
some other value, capital R, that area comes out to be pi times r squared. And that's the formula for the area of a circle. It doesn't matter who you are or what you typically think of math, that right there is a beautiful argument.
It doesn't matter who you are or what you think of math. That right there is a beautiful argument. Nice. I love this.
But if you want to think like a mathematician here,
Hmm.
you don't just care about finding the answer. You care about developing general problem-solving tools
Oh,
and
why did
techniques.
that work?
So take a moment to meditate on what exactly just happened and why it worked. Because the way that we transitioned from something approximate to something precise is actually pretty subtle, and it cuts deep to what calculus is all about. You had this problem that could be approximated with the sum of many small numbers, each of which looked like 2 pi r times dr, for values of r ranging between 0 and 3.
Okay. Okay. So 2 pi r dr. So r is increasing from 0 to 2.9. Yeah. 0.1, 0.2, 0.3, and dr is always 0.1, 0.1, 0.1. Okay, basically dr means r2 minus r1, so increasing by 0.1. We can also do it like if or the more accurate can also be done in a way like this can be 0.5, 0.1, 0.15, 0.2, 0.25, and so on, and the dr will just be 0.5, 0.5, 0. Sorry, 0.0, 0.05, 0.1, 0.15, 0.2, and over here 0.05, 0.05, 0.05. The smaller the dr is, the more accurate the values will be, and if it's really small, then we get the actual area that's given by integral. Yeah.
Remember, the small number dr here represents our choice for the thickness of each ring, for example 0.1. And there are two important things to note here. First of all, not only is dr a factor in the quantities we're adding up, 2 pi r times dr, it also gives the spacing between the different values of r. And secondly, the smaller our choice for dr, the better the approximation. Adding all of those numbers can be seen in a different, pretty clever way.
The better it is, because earlier in the figure as well, so if it was smaller over here in this figure, and then like there would not be any gaps like over here. There are no any gaps because the thickness is smaller. Yeah, so smaller the dr, the nicer it is.
The original. Adding all of those numbers could be seen in a different, pretty clever way as adding the areas of many thin rectangles sitting underneath a graph, the graph of the function 2 pi r in this case. Then, and this is key, by considering smaller and smaller choices for dr, corresponding to better and better approximations of the original problem, the sum, thought of as the aggregate area of those rectangles, approaches the area under the graph. And because of that, you can conclude that the answer to the sum, thought of as the aggregate area of those rectangles, approaches the area under the graph.
I just told that. Yeah.
Because of that,
because if the smaller the dr, the sum approaches the area under triangle. Yeah.
You can conclude that the answer to the original question, in full unapproximated precision, is exactly the same as the area underneath this graph.
Yeah. It was a hard
problem. A lot of other hard problems in math and science
hard problem can be told as sum of many small values.
Be broken down and approximated as the sum of many small quantities. Things like figuring out how far a car has traveled based on its velocity at each point in time. In a case.
Okay, so basically what he means is, so if the velocity changes with respect to time, so all the small distances can be calculated by multiplying velocity at that point and the small distance. Yeah. So integrating from like 0 to some time t, bt dt sums up all the distances, and that helps us find the total distance traveled. Oh, and here's a pi driver.
Case like that, you might range through many different points in time, and at each one multiply the velocity at that time times a tiny change in time, dt, which would give the corresponding little bit of distance traveled during that little time. I'll talk through the details of examples like this later in the series, but at a high level.
Oh, it's the normal distribution, because basically here the distance travel is less and near the middle it's more, again it's less. So basically in on many other fields as well, like the central values tend to have higher frequencies, and it's called normal distribution. It's nice to see it here.
Many of these types of problems turn out to be equivalent to finding the area under some graph. Much the same.
So here, like bt dt was the distance traveled. Over here, like bt is the height, dt is this width, so it's the area. So basically, if we have a velocity time curve, finding just the area under curve is enough to find distance traveled. Yeah.
Same way that our circle problem did. This happens whenever the quantities that you're adding up, the one whose sum approximates the original problem, can be thought of as the areas.
Like if there's the tiny sums are like giving the area, in such cases we can use the integrals.
Many thin rectangles sitting side by side like this. If, finer and finer approximations of the original problem correspond to thinner and thinner rings, then the original problem is going to be equivalent to finding the area under some graph. Again, this is an idea we'll see in more detail later in the series, so don't worry if it's not 100% clear right now.
Yeah, for many of you who are seeing it for the first time, it might not be clear, but yeah, he assures us that he's gonna explain. Let's believe in him.
Is that you, as the mathematician, having just solved a problem by reframing it as the
we are the mathematicians who solve this problem.
area under a graph, might start thinking about how to find the areas under other graphs.
Yeah. Okay. So what do you think? Like here also, like how to find the area. So basically, what we can do is, we can find for x equals to 1, the area we can take it as 1 times 0.1, and then 1.1 square times 0.1 again, and 1.2 square times 0.1, 1.3 square times 0.1. So summing all of those, we can find the area. Yeah. And are there other better ways? He will share us.
I mean, we were lucky in the circle problem that the relevant area turned out to be a triangle.
Yeah, in circle it turned out to be a triangle, but here...
But imagine instead something like a parabola, the graph of x squared. What's the area underneath that curve, say between the values?
Like, is there any other idea other than using integrals? Like, I'm not really sure of that. We can just use integrals from like 0 to whatever this point is, 0 to n x squared dx, and get the answer. But now that he has shared me about the circle's area getting into triangle, I do feel like this area can be represented in some other ways and found out, but I haven't known about that till now. Let's see.
Values of x equals 0 and x equals 3. Well, it's hard to think about, right? And let me reframe that question in a slightly different way. We'll fix that left endpoint in place at 0.
I think he's trying to introduce integrals. I think.
Are you able to find a function, a of x, that gives you the area under this parabola between 0 and x? A function, a of x, like this.
I think he's trying to introduce the derivation that function is just the derivative of area function, or area function is just the antiderivative of the function. I think because that proof is also somewhat similar, because okay, so what you can see is the small area change is actually the function times delta x. Yeah. So if you take delta x to other side, small area change by small delta x is just the function. So if delta x goes to 0, dA by dx is just a function. So you can also see the proof of the fundamental theorem of calculus in this animation as well. Basically, like much of the mathematical complex ideas are hidden in just the figures. So basically, what you can see here is like the dA, the small dA is equal to f times small dx. Yeah. That's why dA by dx equals to f, and that's a very strong proof. And this proof took a lot of time to be found out, but here we can easily find. It's just about the intuitions and visual understanding that matters. And I'm really happy there are people like Grant who are trying to promote this.
Are you able to find a function, a of x, that gives you the area under this parabola between 0 and x? A function, a of x, like this, is called an integral of x squared.
Okay, this was a nice introduction. But if this was, let's say e to the power x, where and e to the power x doesn't go to 0 at x equals to 0, in that point, integral of e to the power x isn't the function that gives area from 0 to x. Yeah, because there's already some area, I think. So let's see.
The tools to figure out what an integral like this is, but right now, it's just a mystery function to us. We know it gives the area under the graph of x squared.
But how do we know that there exist such functions? Maybe there should. I'm not sure. but yeah, okay. So there, okay, he's defining this that there are some function exists which gives us area from 0 to x, and let that be f(x). Yeah, but like, can we be sure that there is such a function? Hmm. Let me check the comments if there are any people. It feels like reaction video. Okay. But I'm not really sure. Like, okay, so there should because a function is just a function. It need not have a pattern. Yeah. Okay, fine. It can. I mean, the polynomial function existence of polynomial function is not sure, but yeah, random function they can be. Okay, fine.
fixed left point and some variable right point, but we don't know what it is. And again, the reason we care about this kind of question is not just for the sake of asking hard geometry questions. It's because many practical problems that can be approximated by adding up a large number of small things can be reframed as a question about an area under a certain graph.
Mm.
And I'll tell you right now that finding this area, this integral function, is genuinely hard. And whenever you come across a genuinely hard question in math, a
You
good
invent
policy
something new. Yeah.
is to not try too hard to get at the answer directly,
Oh.
since usually you just end up banging your head against a
Oh,
wall.
yeah. This is the truth. Like, you don't really get anything by trying too hard to get the answer, but you need to think in a different way, different approach, and try to invent something new. I guess that's one of the secrets. I don't know secrets, but like, I haven't really been able to do such stuff till now. Let's see.
Try too hard to get at the answer directly, since usually you just end up banging your head against a wall. Instead, play around with the idea, with no particular goal in mind.
Yeah,
Spend some
yeah.
time
But yeah, this is the key. But I'm not able to do that.
building up familiarity with the interplay between the function defining the graph, in this case x squared, and the function giving the area.
Oh, there's an ad. There's an ad. Okay.
In that playful spirit, if you're lucky, here's something that you might notice. When you slightly increase x by some
I
tiny
think
nudge,
this is
dx,
he's trying to give the proof of the fundamental theorem of calculus now, and that will be really exciting. Okay.
look at the resulting change in area, represented with this sliver that I'm going to call dA, for a tiny difference in area. That sliver can be pretty well approximated with a rectangle, one whose height is x squared,
Yeah,
and
yeah. I
whose
said
width
this in
is
the beginning.
dx. And the smaller the size of that nudge, dx, the
But the
more
thing
that
is,
sliver
like, when these proofs are on paper with such rigorous claims, yeah, this seem to be boring. But here, like, to be able to see in animated version, it really feels nice.
actually looks like a rectangle.
Yeah.
Now this gives us an interesting way to think about how a of x is related to x squared. A change to the output of a, this little dA, is about equal to x squared, where x is whatever input you started at, times dx, the little nudge to the input that caused a to change. Or rearranged, dA divided by dx, the
Yeah,
ratio of a
and
tiny
this
change in
is
a
the
to the
biggest
tiny change
discovery
in
in
x that caused
calculus.
it, is approximately whatever x squared is at that point. And that's an approximation that should get better and better for smaller and smaller choices of dx. In other words, we don't know what a of x is. That remains a mystery. But we do know a property that this mystery function must have. When you look at two nearby points, for example 3 and 3.001, consider the change to the output of a between those 2 points. The difference between the mystery function evaluated at 3.001 and evaluated at 3. That change, divided by the difference in the input values, which in this case is 0.001,
That should be x
should
squared.
be about equal to the value of x squared for the starting input, in this case 3 squared.
Yeah.
And this relationship between tiny changes to the mystery function and the values of x squared itself is true at all inputs, not just 3. That doesn't immediately tell us how to find a of x, but it provides a very strong clue that we can work with.
Yeah.
And there's nothing special about the graph x squared here. Any function, defined as the area under some graph, has this property, that dA divided by dx, a slight nudge to the output of a, divided by a slight nudge.
Like, these things aren't really anything new that he discovered, but like redesigning the way we first look at them. Yeah, I mean rephrasing the way that we have been introduced to it. This really helps to get the intuition. Yeah, though it's not new, but it's different.
Nudge to the input that caused it is about equal to the height of the graph at that point.
Mhm.
Again, that's an approximation that gets better and better for smaller choices of dx. And here, we're stumbling into another big idea from calculus: derivatives. This ratio, dA divided by dx, is called the derivative of a, or more
Okay,
technically,
so
the
here's the
derivative.
definition of derivative as well. Okay, so you first define integration and then only define derivative. But that's is that the way they were introduced to maths? I'm not really sure, but yeah, fine. Because mostly in textbooks we are first introduced derivatives and the integral as the opposite of derivative, antiderivative. Yeah, and that's not really the best way. This one is cool.
Is whatever this ratio approaches as dx gets smaller and smaller.
Mm.
I'll dive much more deeply into the idea.
Okay, the paradox of the derivative. I haven't really heard of this till now, but I think it will be fun to watch this video. So s of t plus dt. It's fine. I have heard of this, I guess. But the paradox, like I'm not really seeing this as a paradox. Let's see how does this go.
Idea of a derivative in the next video. But loosely speaking, it's a measure of how sensitive a function is to small changes in its input. You'll see as the series goes on that there are many, many ways that
Okay, so this one is basically what was this product rule?
you can visualize a derivative, depending on what function you're looking at and how you think about tiny nudges to its output.
Yeah, x
Care about derivatives because they help us solve problems. And in our little exploration here, we are a glimpse of one way that they're
yeah,
used.
so we basically proved
They
the most powerful thing at first, and then we are now going to basics.
are the
Nice.
key to solving integral questions,
Mm.
problems that require finding the area under a curve. Once you gain enough familiarity with computing derivatives, you'll be able to look at a situation like this one, where you don't know what a function is, but you do know that its derivative should be x squared, and from that, reverse engineer what the function must be.
Yeah, reverse engineer what the function must be.
And this back and forth between integrals and derivatives, where the derivative of a function for the area under a graph gives you back the function defining the graph itself, is called the fundamental theorem of
Yeah, the
calculus.
fundamental theorem of calculus. Nice.
It ties together the two big ideas of integrals and derivatives, and it shows how, in some sense, each one is an inverse of the other.
Yeah.
All of this is only a high-level view, just a peek
Yeah,
at
this
some
is
of the
just a
core
peek.
ideas
We haven't really gone into details, and there are 9 more videos to go into that. Yeah, it will be fun.
that emerge in calculus. And what follows in this series are the details for derivatives and integrals and more. At all points, I want you to feel that you could have invented calculus
Yeah.
yourself.
This is the much like nicer thing, that he would make us feel that we have the invented calculus yourself. Just like that proof of fundamental theorem of calculus, that is also like we seeing it ourselves rather than like proof from somebody else. Like we saw it ourselves even before he told it. Yeah. So this is what feels like inventing calculus, and he's gonna show us more.
That if you drew the right pictures and played with each idea in just the
Yeah,
right
if
way,
you drew the right pictures, yeah.
these formulas and rules and constructs that are presented could have just as easily popped out naturally from your own explorations.
Mm.
And before you go, it would feel wrong not to give the people who supported this series on Patreon a well-deserved thanks, both for their financial backing as well as for the
Okay, thanks
suggestions
to
they
this
gave
video.
while the
Thanks to
series was
these
being
people as well.
developed. You see, supporters got early access to the videos as I made them, and they'll continue to get early access for future Essence of type series. And as a thanks to the community, I keep ads off of new videos for their first month. I'm still astounded that I can spend time working on videos like these, and in a very direct way, you are the one to thank for that.
Okay. Before we begin next video, let me drink some water. The paradox of the derivatives. Nice.
If you have a live chat on your website, but you're not able to respond within 30 to 60 seconds, you
Okay, let's go into this one. So far as the theories of mathematics are about reality, they are not certain. So far as they are certain, they are not about reality. Ah, nice. Because reality is never certain. Yeah. Okay, so first of all,
The goal here is simple. Explain what a derivative is.
okay,
The
what
thing
the
is, though, there's some subtlety to this topic, and a lot of potential for paradoxes if you're not careful. So kind of a secondary goal is that you have an appreciation for what those paradoxes are and how to avoid them.
okay, non-derivatives, avoid paradoxes. Yeah. Basically, I think the 0 by 0 form is the paradox that he's talking about. Yeah, but I'm not really sure because I haven't watched it. But I think that indeterminate is the one that he talks about.
You see, it's common for people to say that the derivative measures an instantaneous rate of change. But
Hmm.
when you think about it, that phrase is actually an oxymoron. Change is something that happens between
What did
separate.
you
About
say?
it, that phrase is actually
Oxymoron. What's that oxymoron? Let me search it. Oxymoron. Figure of speech in which apparently contradictory terms appear in conjunction. Okay, I did not get this, but it doesn't matter.
an oxymoron. Change is something that happens between separate points in time. And when you blind yourself to all but just a single instant, there's not really any room for change. You'll see
Nice. If you plug this to a very small instant, there's no any time for change. That was nice.
what I mean more as we get into it, but when you appreciate that a phrase like instantaneous rate of change is actually nonsense, I think it makes you appreciate just how clever the fathers of calculus were in capturing the idea that that phrase is meant to.
Okay, so this feels nonsense to us, but there are people like Barrow, Newton, Leibniz, Cauchy, Weierstrass, who made sense of these things. I think I can take a screenshot of these people. Okay.
Evoke, but with a perfectly sensible piece of math, the derivative.
Okay, so basically these three people discovered it. I never heard about this man Barrow. Okay. And Cauchy and Weierstrass made it rigorous. Nice.
As our central example, I want you to imagine a car that starts at some point A, speeds up, and then slows down to a stop at some point B 100 meters away. And let's say it all happens over the course of 10 seconds. That's the setup to have in mind as we lay out what the derivative is. We could graph this motion, letting the vertical axis represent the distance traveled and the horizontal axis represent time. So at each time t, represented with a point somewhere on this horizontal axis, the height of the graph tells us how far the car has traveled in total after that amount of time.
Okay, so this is how far the car is at time t, yeah, from the initial position. And note that this isn't going down because the car never like went back, it only went like forwards, so it is always going up, yeah.
It's pretty common to name a distance function like this s of t.
Mm.
I would use the letter d for distance, but that guy already has another full-time job in calculus.
Okay, so
Initially, this
if
curve
you write
distance,
this
but
as
that guy
dt also means that small change in t, so let's write this as of
already
t.
has another full-time job in calculus.
Full time job in calculus, nice.
Initially, this curve is quite shallow, since the car is slow to start. During that first second, the distance that it travels doesn't really change that much. Then, for the next few seconds, as the car speeds up, the distance traveled in a given second gets larger, which corresponds.
Okay, so distance travel is basically this height, yeah, yeah. From t equals to 4 to t equals to 5, it goes from 30 meter away to 50 meter away. So distance travel is 20. Yeah, fine.
To a steeper slope in this graph.
Okay, and the instantaneous velocity should be just basically average velocity is kind of the distance traveled by time taken. So if this gap is really small and we take small distance by small time, that should be the instantaneous velocity, I guess.
And then towards the end, when it slows down, that curve shallows out again. And if we were to plot the car's velocity in meters per second,
Okay, so he carved the car for velocity. Okay, so basically, how do you know that velocity is maximum at this point? Okay, so because for the small time change, like the distance travel is huge over here. Over here, basically, the slope of this line, because distance traveled by time taken, yeah, the height is distance traveled and this is time taken. So instantaneous velocity is when like the slope is higher, the distance traveled is higher. That's why velocity is also higher at those points. But over here, very small distance traveled, very small, so velocity is also small. Basically, this graph is just the graph of the slope of the function over here as of t, yeah.
as a function of time, it might look like this bump. At early times, the velocity is very small. Up to the middle of the journey, the car builds up to some maximum velocity, covering a relatively large distance each
Yeah.
second. Then it slows back down towards a speed of 0.
Mm-hmm.
And these two curves here are definitely related to each other, right? If you change the specific distance versus time function, you're going to have some different velocity versus time function. And what we want to understand is the specifics of that relationship. Exactly how does velocity depend on a distance versus time function?
Okay, so how does velocity depend upon the distance versus time function? Yeah, that's a nice good question to get adapted with derivatives.
And to do that, it's worth taking a moment to think critically about what exactly velocity means here. Intuitively, we all might know what velocity at a given moment means. It's just whatever the car's speedometer shows in that moment.
Okay.
And intuitively, it might make sense that the car's velocity should be higher at times when this distance function is steeper, when the car
Yeah.
traverses more distance per unit time.
Mm.
But the funny thing is, velocity at a single moment makes no sense. If I
Yeah,
show you
like
a
in a
picture
very
of a
short time, there will be no distance traveled. Yes, so that's why it's 0 by 0. But we construct it short enough such that it isn't really 0. Like very small change, limits. Yeah.
car, just a snapshot in an instant, and I ask you how fast it's going, you'd have no way of telling me. What you'd need are two separate points in time to compare.
Yeah.
That way you can compute whatever the change in distance across those times is, divided by the change in time. Right? I mean, that's what velocity is. It's the distance traveled per unit time. So how is it that we're looking at a function for velocity that only takes in a single value of t, a single snapshot in time? It's weird, isn't it? We want to associate
This is actually weird because for a single moment, like we won't really be able to find because there's no distance traveled. But we have the tools like derivatives, like that. In fact, like consider very small, this is 0.000000001, and that's as small as 0, and we can use that. So yeah, now it seems like it's a paradox. Yeah.
individual points in time with a velocity, but actually computing velocity requires in times. If that feels strange and paradoxical, good.
Yeah, it
You're
feels-
grappling with the same conflicts that the fathers of calculus did.
Okay.
And if you want a deep understanding for rates of change, not just for a moving car, but for all sorts of things in science, you're going to need to resolve this apparent paradox.
Yeah.
First, I think it's best to talk about the real world, and then we'll go into a purely mathematical one. Let's think about what the car's speedometer is probably doing. At some point, say 3 seconds into the journey, the speedometer might measure how far the car goes in a very small amount of time. Maybe the distance traveled between 3 seconds and 3.01 seconds.
Yeah.
Then it could compute the speed in meters per second as that tiny distance traversed in meters divided by that tiny time,
Yeah.
0.01 seconds.
Okay, so this is basically
That
the
is-
definition of derivative itself. Time change in function by time change in time.
A physical car just sidesteps the paradox and doesn't actually compute speed at a single point in time. A physical car just sidesteps
A physical car just side steps the paradox.
and doesn't actually
doesn't actually compute speed at a single point in time, but instead takes two times which are very closer to each other and finds the speed. Yeah.
compute speed at a single point in time. It computes speed during a very small amount of time.
Okay, so this is not
So
instantaneous.
let's call that difference in
Nice.
time dt, which you might think of in this case as 0.01 seconds. And let's call that resulting difference in distance ds. So the velocity at some point in time is ds divided by dt, the tiny change in distance over the tiny change in time.
Yeah.
Graphically, you can imagine zooming in on some point of this distance versus time graph above t equals 3. That dt is a small step to the right, since time is on the...
Yeah.
And that ds is
So
the
he's showing
resulting
that it
change
is
in the
got slope
height of
now.
the graph, since the vertical axis represents the distance traveled. So ds divided by dt is something you can think of as the rise over run slope between two very close points on this graph. Of course, there's nothing special about the value t equals 3. We could apply this to any other point in time, so we consider this expression ds over dt to be a function of t, something where I can give you a time t and you can give me back the value of this ratio at that time, the velocity as a function of time. So, for example, when I had the computer draw this bump curve here, the one representing the velocity function, here's what I had the computer actually do. First, I chose a small value for dt. I think in this case it was 0.01. Then I had the computer look at a whole bunch of times t between 0 and 10 and compute the distance function
Okay,
s
so basically,
as t
I
plus
do think that
dt.
his computer should be able to find integral equation in a quite nicer way, and then just plot the integral equation. But for the sake of understanding, he's trying to give us the definition of the derivative. Yeah, s of t plus dt minus s of t, yeah, which is rise and over dt, that is run. So he is trying to give us the definition of derivative in the first principle way.
And then subtract off the value of that function at t. In other words, that's the difference in the distance traveled between the given time t and the time 0.01 seconds after that. Then you can just divide that difference by the change in time, dt, and that gives you velocity in meters per second around each point in time. So with a formula like this, you could give the computer any curve representing any distance function s of t, and it could figure out the curve representing velocity. So now would be a good time to pause, reflect, make sure that this idea of relating distance to velocity by looking at tiny changes
Now
makes
it's the
sense.
time to find out how do we get the equation of this curve. Now that we can find all the values and plot all the values and get a curve, now it's time to find out how to get the equation of that curve. Yeah.
Because what we're going to do is tackle the paradox of the derivative head on.
Oh, nice.
This idea of ds over dt, a tiny change in the value of the function s divided by the tiny change in the input that caused it, that's almost what a derivative is. And even though a
Like,
car's
why did you say it
positive,
as almost? Isn't this what the derivative is? I don't know. Let's see.
that's almost what a derivative is. And even though a car's speedometer will actually look at a concrete change in time, like 0.01 seconds, and even though the drawing program here is looking at an actual concrete change in time, in pure math, the derivative is not this ratio ds dt for a specific choice of dt. Instead, it's whatever
in
that
pure
ratio
math,
approaches
It's
as
very
the choice for dt
small
approaches
delta t
0.
where it goes to 0. Yeah.
Luckily, there is a really nice visual understanding for what it means to ask what this ratio approaches. Remember, for any specific choice of dt, this ratio ds dt is the slope of a line passing through two separate points on the graph, right? Well, as dt approaches 0, and as those 2 points approach each other, the slope of the line approaches the slope of a line that's tangent to the graph at whatever point t we're looking at. So the true, honest-to-goodness, pure math derivative is not the rise over run slope between two nearby points on the graph. It's equal to the slope of a line tangent to the graph at a single point. Now, notice what I'm not saying.
If it goes to 0, it's equal to the slope of the tangent itself, not just the rise over run.
I am not saying that the derivative is whatever happens when dt is infinitely small, whatever that would mean. Nor am I saying that you plug in 0 for dt. This dt is always a finitely small, non-zero value. It's just that it approaches 0 is all.
Yeah. Infinitely small non.
I think that's really clever.
That's really
Even though change in an
awesome.
instant makes no sense, this idea of letting dt approach 0 is a really
Okay, so in
sneaky
this way,
backdoor.
we are really letting dt approaches as small as 0, yeah.
way to talk reasonably about the rate of change at a single point in time. Isn't that neat? It's kind of flirting with the paradox of change in an instant without ever needing to actually touch it. And it comes with such a nice visual intuition too, as the slope of a tangent line to a single point on the graph. And because change in an instant still makes no sense, I think it's healthiest for you to think of this slope not as some instantaneous rate of change, but instead as the best constant approximation for a rate of change around a point.
Okay. It's helpful to think as slope, yeah.
By the way, it's worth saying a couple words on notation here. Throughout this video, I've been using dt to refer to a tiny change in t, with some actual size, and ds to refer to the resulting change in s, which again has an actual size. And this is because that's how I want you to think about them. But the convention in calculus is that whenever you're using the letter d like this, you're kind of announcing your intention that eventually you're going to see what happens as dt approaches 0. For example, the honest-to-goodness pure math derivative is written as ds divided by dt, even though it's technically not a fraction per se, but whatever that fraction approaches for smaller and smaller nudges in t.
Okay, so there's an add.
I think a specific example should help here. You might think that asking about what this ratio approaches for smaller and smaller values would make it much more difficult to compute. But weirdly, it kind of makes things easier. Let's say that you have a given distance versus time function that happens to be exactly t cubed.
I think now he's going to derive the derivative of t cube, yeah, with that first principle definition, let's say.
So after 1 second, the car has traveled 1 cubed equals 1 meters. After 2 seconds, it's traveled 2 cubed, or 8 meters, and so on. Now what I'm about to do might seem somewhat complicated, but once the dust settles, it really is simpler. And more importantly, it's the kind of thing that you only ever have to do once in calculus. Let's say you wanted to compute the velocity, ds divided by dt, at some specific time, like t equals 2. And for right now, let's think of dt as having an actual size, some concrete nudge. We'll let it go to 0 in just a bit. The tiny change in distance between 2 seconds and 2 plus dt seconds, well, that's s of 2 plus dt minus s of 2. And we divide that by dt. Since our function is t cubed, that numerator looks like 2 plus dt cubed minus 2 cubed.
Okay, I think
and this
is gonna do
is something we can work out algebraically.
But with numbers.
Again, bear with me. There's a reason that I'm showing you the details here. When you expand that top, what you get is 2 cubed plus 3 times 2 squared dt
plus 3
plus
times
3
2
times 2
square
times dt squared
plus dt cubed
plus dt cubed, and all of that is minus 2 cubed. Now there's a lot of terms, and I want you to remember that it looks like a mess, but it does simplify. Those 2 cubed terms, they cancel out. And then everything remaining here has a dt in it. And since there's a dt on the bottom there, many of those cancel out as well. What this means is that the ratio ds divided by dt has boiled down into 3 times 2 squared plus, well, 2 different terms that each have a dt in them.
Okay,
so if we ask what happens as dt approaches 0, representing the idea of looking at a smaller and smaller change in time, we can just completely ignore those other terms. By eliminating the need to think about a specific
if dt is like somewhat 0.1, and in that case, if you want to find the slope of the secant, or let's say the rise over run, then you can include dt as 0.1 and then find it. But now in this case, if you want to find slope of tangent, then they're just as equal as 0. You can remove them, yeah.
We've actually eliminated a lot of the complication in the full expression. So what we're left with is this nice clean 3 times 2 squared. You can think of that as meaning that the slope of a line tangent to the point at t equals 2 of this graph is exactly 3 times 2 squared, or 12. And of course, there's nothing special about the time t equals 2. We could more generally say that the derivative of t cubed as a function of t is 3 times t squared.
Yeah, there's nothing special about t. I knew that he's gonna replace like 2 by t at some point and now find the derivative function of t cubed, yeah.
Now take a step back, because that's beautiful.
That's beautiful.
The derivative is this crazy complicated idea. We've got tiny changes in distance over tiny changes in time, but instead of looking at any specific one of those, we're talking about what that thing approaches.
Though
I mean,
it feels like quite trivial stuff, quite easier for now, but for those people who actually invented it, like this was unthinkable for that time. But now it's really trivial. Yeah.
that's a lot to think about.
Mm.
And yet what we've come out with is such a simple expression, 3 times t squared.
Mm.
And in practice, you wouldn't go through all this algebra each time. Knowing that the derivative of t cubed is 3t squared is one of those things that all calculus students learn how to do immediately without having to rederive it each time.
Yeah.
And in the next video, I'm going to show you a nice way to think about this and a couple other derivative formulas in really nice geometric ways.
Yeah.
But the point I want to make,
Yeah, that symmetric way, I think that's really cool.
by showing you all of the algebraic guts here, is that when you consider the tiny change in distance caused by a tiny change in time for some specific value of dt, you'd have kind of a mess. But when you consider what that ratio approaches as dt approaches 0, it lets you ignore much of that mess, and it really does simplify the problem.
Yeah.
That right there is kind of the heart of why calculus becomes useful. Another reason to show you a concrete derivative like this is that it sets the stage for an example of the kind of paradoxes that come about if you believe too much in the illusion of instantaneous rate of change.
Okay, so we did get the paradox, yeah, because the word instantaneous is kind of big, and that creates the paradox. Yeah.
So think about the actual car traveling according to this t cubed distance function, and consider its motion at the moment t equals 0, right at the start. Now ask yourself whether or not the car is moving at that time. On the one hand, we can compute its speed at that point using the derivative, 3t squared, which for time t equals 0 works out to be 0. Visually, this means that the tangent line to the graph at that point is perfectly flat, so the car's quote-unquote instantaneous velocity is 0, and that suggests that obviously it's not moving. But on the other hand, if it doesn't start moving at time 0, when does it start moving? Really, pause and ponder that for a moment. Is the car
That was
moving?
such a wonderful question. If it's not moving at t equals 0, when is it? At t equals 0.0000000000001, yeah, at that point it's moving. But how do you write that? We can write that by a limit t tends to 0 plus of 1 by t. Sorry, limit t tends to 0 plus of t, yeah. So limits come to be helpful in such cases, and that's really nice question to invent limits, yeah.
Moving at time t equals 0. Do you see the paradox? The issue is that the question makes no sense. It references the idea of change in a moment, but that doesn't actually exist. That's just not what the derivative measures. What it means for the derivative of a distance function to be 0 is that the best constant approximation for the car's
best constant approximation, yeah. Basically, if it was, let's say, for t equals to 2, like we might find the answer to be 12.000001, but
velocity.
the base constant approximation is 12, which can be found by the formula, yeah, 3 times 2 square. Okay, so that's a really nice idea.
Around that point is 0 meters per second. For example, if you look at an actual change in time, say between time 0 and 0.1 seconds, the car does move. It moves 0.001 meters. That's very small. And importantly, it's very small compared to the change in time, giving an average speed of only 0.01 meters per second.
Okay, so this is between t equals to 0 and t equals 0.1, okay. Yeah.
And remember, what it means for the derivative of this motion to be 0 is that for smaller and smaller nudges in time, this ratio of meters per second approaches 0.
So basically derivative is not the instantaneous measure, but derivative is the base constant approximation, yeah. And now since the actual value is 0.0000001, so this new definition that it's constant approximation, the approximation should go to 0, yeah. So now this new definition makes sense, yeah.
But that's not to say that the car is static. Approximating its movement with a constant velocity of 0 is, after all, just an approximation. So whenever you hear people refer to the derivative as an instantaneous rate of change, a phrase which is intrinsically oxymoronic, I want you to think of that as
Oxymoron.
a conceptual shorthand for the best constant approximation for rate of change.
Yeah.
In the next couple of videos, I'll be talking more about the derivative, what it looks like in different contexts, how do you actually compute it, why is it useful, things like that, focusing on visual intuition as always.
Okay, so we complete the second video as well. Now before we start third one, let me drink water again. No, this is derivative formulas through geometry. Okay, so third video I think I have the idea about that. But fourth one, visualizing the chain rule, like I've never seen of that. I think that will be interesting for me as well. Yeah. Okay. I think the length of the videos are really long, 17-16 minutes. I think. How are others? Okay, so it's the same for all of them, but yeah, we are enjoying this. Derivative formulas through geometry. You know, for a mathematician, he did not have enough imagination, but he has become a poet and now he is fine. Okay, who was the one who told this? David Hilbert. Oh, there are a lot of quotes from Hilbert in this series. You know, for a mathematician, he did not have enough imagination, but he has become a poet and now he is fine. Okay, so poet has a lot of imaginations, but I didn't understand this quotation. Fine.
Now that we've seen what a derivative means and what it has to do with rates of change, our next step is to learn how to actually compute these guys. As in, if I give you
We
some kind
actually
of
compute like for x cube, yeah, already. Now, let us see how do we compute this for all things. And for this, we need some tools like a product rule, and then chain rule, power rule, quotient rule, and I think he is gonna derive those rules over here.
function with an explicit formula,
When was
you'd
this
want to be
video
able to
posted on YouTube? 6 years ago. Oh, that means like when I was learning calculus 3 years back, it was already there, but I never knew. Like I learned it from Don't Memorize. That was also nice, but this was already there. Wow, why did I miss this? Fine.
find what the formula for its derivative is. Maybe it's obvious, but I think it's worth stating explicitly why this is an important thing to be able to do. Why much of a calculus student's time ends up going towards grappling with derivatives of abstract functions rather than thinking about concrete rate of change problems. It's because a lot of real-world phenomena, the sort of things that we want to use calculus to analyze, are modeled using polynomials, trigonometric functions, exponentials, and other pure
Yeah, because mathematical modeling, these functions do come, so that's why we need to be able to solve them. Yeah.
functions like that. So if you build up some fluency with the ideas of rates of change for those kinds of pure abstract functions, it gives you a language to more readily talk about the rates at which things change in concrete situations that you might be using calculus to model. But it is way too easy for this process to feel like just memorizing a list of rules. And if that happens, if you get that feeling, it's also easy to lose sight of the fact that derivatives are fundamentally about just looking at tiny changes to some quantity and how that relates to a resulting tiny change in another quantity. So in this video and in the next one, my aim is to show you how you can think about a few of these rules intuitively and geometrically. And I really want to...
Whoa. I have seen some glimpse of the visual proof of the derivative of sine theta, yeah, but I have not really seen it a lot. Okay. So before we like go into this amazing thing, let me first go to restroom and I will return back. Yeah. Just some time. So I'm back, and now we are going to see some visual proofs of different identities such as sign accents, the proof of the different formulas. Okay, so that's gonna be a really cool time. And what's this over here? So this is actually for a product. XDX would be XDX. Nice.
To show you how you can think about a few of these rules intuitively and
Geometrically. Basically, this has already interested me. Like, how is he gonna do that? So f of theta equals sine theta. Sine theta is gonna give the height for corresponding this, and this is theta, small theta. Small change in height by small theta. Okay, so basically, small change in height is this thing, and a small theta is this thing. Is this the thing? Small theta? No. No. What's a small theta? Okay. So if there's a small change in theta, del theta. So this is tangent, yeah, 90 degrees. Theta. This is height. So shall we try to do it, or was it? Let me try to do it first on my own, like how to find the derivative of sine theta visually, and then we will go to video, yeah, because it's better to first try it yourself before we watch it. Yeah. Let's try to do this. Okay, so we are trying to find it takes some time. Okay, but you can wait. Okay. Syncing your latest whiteboards. Okay, start now. Let's do it. So basically, we have a circle. Let me not make it. Let me make it slightly thinner. Okay, we have a circle. Yeah. And basically, if this is the center, we want to find derivative of sine theta. Okay. Theta equals sine theta. Sine theta is basically this height over here. Okay, so for that, this needs to be a unit circle. So let's suppose that this is a unit circle. Yeah, then if this is theta, and this theta is in radians, yeah. If this is theta, now this height over here is just sine theta. Now, let's say we have some del theta. Okay. So in that case, okay. So basically, okay. So this is the del f, yeah, change in the function, because the new height is this thing, yeah. And like, how do we now take the theta to? Where do we take the theta to? So let's say this is a tangent line. Theta 90 minus theta. I think the theta will go over here. Okay, because if this is a tangent line, yeah. Oh wait, and those are just perpendicular. Wait. Okay, so if it's theta, there will 90 minus theta, and okay, this will be theta again. Yeah, that will be 90 minus theta again. Yeah, and then 90. Okay, then so 90 minus theta, and then if that's the theta. Okay, this over here will again be 90 minus theta, and then it's a unit circle. Okay. This figure isn't really clear. I think we'll discover it in the middle of the video. Let's try.
Geometrically. And I really want to encourage you to never forget that tiny nudges are at the heart of derivatives. Let's start with the simple function.
Oh,
Tiny nudges.
is this the d theta? Okay, if it's in radian, now this is just the theta. Yeah. Okay, so let me do it again. Now I think if it's in radian, then the angle theta over here in radians, and this length is just the theta. Okay, for radian measure, and derivative is also for only for radian measure, not for degrees. Yeah. Now in that case, this will just be our del theta. Yeah, and this is just gonna be our del of f. Okay. Now if this is theta, this over here is 90 minus theta. Again, this is theta, 90 minus theta, and then theta. So this angle over here will be theta. So now del f by del theta. Yeah, now I think I get it. Del, but I'm not really sure though. Still I'm not sure. Okay, yeah, del f by now this del theta is now hypotenuse, del f is perpendicular, and this thing over is base. Now del f by del theta is just base by hypotenuse, so that's cos theta. So you can see that df by d theta is cos theta. Okay, we did prove this finally. Okay, so basically, if you are still confused, so what happened is, so this thing over here is basically the change in height, and this thing over here is change in theta. Yeah, and because this angle is 90 minus theta. Yeah, so this one is theta, 90 minus theta, this is theta. So now cos theta equals to base by height, and base is just df by d theta. So df by d theta is just cos theta. So we get it that way. Yeah, now but now let's see the video.
Are at the heart of derivatives. Let's start with a simple function, like tiny nudges are at the heart of derivatives.
Yeah.
Let's start with a simple function, like f of x equals x squared. What if I asked you its derivative? That is, if you were to look at some value x, like x equals 2, and compare it to a value slightly bigger, just dx bigger, what's the corresponding change in the value of the function? Df. And in particular, what's df divided by dx? The rate at which this function is changing per unit change in x. As a first step for intuition, we know that you can think of this ratio df dx as the slope of a tangent line to the graph of x squared. And from that, you can see that the slope generally increases as x increases. At 0, the tangent line is flat, and the slope is 0. At x equals 1, it's something a bit steeper. At x equals 2, it's steeper still. But looking at graphs isn't generally the best way to understand the precise formula for a derivative. For that, it's best to take a more literal look at what x squared actually means. And in this case, let's go ahead and picture a square whose side length is x. If you increase x by some tiny nudge, some little dx...
But like over here, like let me give you a glimpse of what he's gonna say. But like if I give that right now, then it wouldn't really fun for you to watch. Yeah, but still let me give it. So like he's just now trying to give it for x square. Yeah. Now change in x square, uh, change in the entire function x square is just x times dx, this area over here, yeah, and then this area also x times dx and dx whole square. Yeah, so basically it's 2x dx plus dx whole square. But this can also be told for the product rule, when if this was f, if this was g, and this should have just been del g, this should have just been del f, and so the derivative of fg would be this thing f del g plus g del f plus del f del g. Yeah, basically this same setup is also the proof for product rule. Now we can prove the product rule from this expression as well. But yeah, this can also used to find the derivative of x squared, because this is also product of x and x. Yeah, let's see how he does it.
What's the resulting change in the area of that square? That slight change in area is what df means in this context. It's the tiny increase to the value of f of
that slight change in area is what df means in this context.
x equals x squared, caused by increasing x by that tiny nudge dx. Now you can see that there's 3 new bits of area in this diagram. 2 thin rectangles and a minuscule square. The
so
2 thin rectangles
from this
each
video,
have...
he's trying to give us a different interpretation of derivative rather than from the graph only. So earlier he gave us from the velocity of perspective from the graph, and now he's trying to give us different interpretations so as to derive the formulas. Yeah,
side lengths of x and dx, so they account for 2 times x times dx units of new area. For example, let's say x was 3 and dx was 0.01, then that new area from these 2 thin rectangles would be 2 times 3 times 0.01, which is 0.06, about 6 times the size of dx. That little square there has an area of dx squared, but you should think of that as being really tiny, negligibly tiny. For example, if dx was 0.01, that would be only 0.0001. And keep in mind, I'm drawing dx with a fair bit of width here just so we can actually see it, but always remember, in principle, dx should be thought of as a truly tiny amount. And for those truly tiny amounts, a good rule of thumb is that you can ignore anything that includes a dx raised to a power greater than 1. That is, a tiny change squared is a negligible change. What this leaves us with is that df is just some multiple of dx. And that multiple, 2x, which you could also write as df divided by dx, is the derivative of x squared. For example, if you were starting at x equals 3, then as you slightly increase x, the rate of change in the area per unit change in length added, dx squared over dx, would be 2
change in area per unit change of x. That's just
times
dx
3,
by dx.
or 6. And if instead you were starting at x equals 5, then the rate of change would be 10 units of area per unit change in x.
10. Okay, so per unit change in x. Okay, directly did it for derivative, or did not show it numerically, just did it. Okay, fine. Basically over here, like if the change was 0.1, so basically it means to say that 2 into 3 into 0.1 by 0.1, and 0.1 cancels out, so 2 into 3. Yeah, that's fine. He could have shown it numerically as well for this case as well, but he
at x equals 3, then as you slightly increase x, the rate of change in the area per unit change in length added, dx squared over dx, would be 2 times 3, or 6. And if instead you were starting at x equals 5, then the rate of change would be 10 units of area per unit change in x.
Yeah, per unit change in x, we can easily find out how many changes in area it would be using differentiation, and that's the power.
Let's go ahead and try a different simple function.
Okay.
F of x equals x cubed.
Oh, nice. Now
this is going to be the geometric view of the stuff that I went through
yeah.
algebraically in the last video.
That's nice.
What's nice here is that we can think of x
cubed is
cubed
going to do for x to the power 4. Use a 4-dimensional box.
As the volume of an actual cube, whose side lengths are x. And when you increase x by a tiny nudge, a tiny dx, the resulting increase in volume is what I have here in yellow. That
Okay,
represents
so this is gonna be like in this box over here, this box over here, and this box over here. There are three boxes that increase, and the area of each of them is just x, x, and dx, x, x, dx, x, x, dx. So 3 x squared dx, that means 3x squared dx will be the derivative, yeah. And that's a really nice way to think about it. And you can also like going beyond these cubes and squares, like it seems really powerful when you go to spheres, yeah. And basically if you are in spheres, then it seems to be more powerful. So let's say we have a sphere whose volume is given by 4 by 3 pi r cube, yeah. Now if you change its radius by a tiny amount, like just a outside layer is going to be added in that volume, just the outside layer, which means like a slight surface area, that means the total surface area times dr, that's gonna be increased, yeah. So the outside surface area is just 4 pi r square like times dr, so that's gonna be the increase in volume. And guess what, that is just the dB. Now if you try to differentiate this, try to find the dB by dr, that's just 4 by 3 times 3 pi r square. And you see, like you could actually found it out just from the intuition itself without going into a lot of calculative details, yeah. So there are such powerful interpretations. You can try to find others as well, and he is trying to share here about the cube and squares, and that's really nice.
all the volume in a cube with side lengths x plus dx that's not already in the original cube, the one with side length x. It's nice to think of this new volume as broken up into multiple components.
Yeah.
But almost all of it
And
comes from
in this case, like even these lines, like which were previously considered to be not negligible, now even these will be negligible because we have big rectangles over here, like whose because of those, these lines will be negligible, and this point will also be negligible.
these three square faces. Or, said a little more precisely, as dx approaches 0, those three squares comprise a portion closer and closer to 100% of that new yellow volume.
Yeah. When dx goes to 0, like those three are the one that dominate.
Each of those thin squares has a volume of x squared times dx, the area of the face times that little thickness dx. So in total, this gives us
Now, like
3x
you might be
squared.
wondering, like why did he not increase over here or in the downside on the other side? Yeah, but the thing is, like in length, if you are increasing length by dx, you can either do in left or right only, not in both sides. If you are increasing height by dx, you can do either in up or down side, not in both sides. Similarly, over here in breadth as well. So that's why we can do it in only one side and not both sides. That's the answer.
dx of volume change. And to be sure, there are other slivers of volume here along the edges and that tiny one in the corner, but all of that volume is going to be proportional to dx squared, or dx cubed, so we can safely ignore them. Again, this is ultimately because they're going to be divided by dx. And if there's still any dx remaining, then those terms aren't going to survive the process of letting dx approach 0. What this means is that the derivative of x cubed, the rate at which x cubed changes per unit change of x, is 3 times x squared. What that means in terms of graphical intuition is that the slope of the graph of x cubed at every single point x is exactly 3x squared. And reasoning about that slope, it should make sense that this derivative is high on the left, and then 0 at the origin, and then high again as you move to the right.
Yeah, this makes sense because basically if it was 3x square, yeah. Basically because it's a positive number, it's always positive because 3x square is positive and slope is always positive, and also it's really less when x is in between -1 to 1 for less parallels of x, and when x increases, slope is also increasing on both the sides, and when x is 0, the slope is 0, and so the line is parallel to x-axis. Yeah, so you can observe those facts.
But just thinking in terms of the graph would never have landed us on the precise quantity 3x
Yeah,
squared.
like sometimes you need to go beyond the graph. So we introduce all of them with the graphs, yeah, but it's never really like helpful to stick in one definition. You should try to expand your horizons and think from different perspectives in math to discover something new. Like I can also tell these things to others, but personally, like even like I'm also facing difficulty doing this, yeah. And those who do this, they are gonna break barriers, yeah.
For that, we had to take a much more direct look at what x cubed actually means. Now, in practice, you wouldn't necessarily think of the square every time you're taking the derivative of x squared,
Yeah.
nor would you necessarily think of this cube whenever you're
There's
taking
a
the
general
derivative
rule.
of x cubed. Both of them fall under a pretty recognizable pattern for polynomial terms. The derivative of x to the fourth turns out to be 4x cubed. The derivative of x to the fifth is 5x to the fourth, and so on. Abstractly,
So you
you'd
might
write
notice
this
a
as
pattern.
the derivative of x to the n, for any power n, is n times x to the n minus 1.
Yeah.
This right here is what's known in the business as the power rule.
Wow, rule.
In practice, we all quickly just get jaded and think about this symbolically, as the exponent hopping down in front, leaving behind one less than itself, rarely pausing to think about the geometric delights that underlie
Yeah,
these
yeah.
derivatives.
While learning these things, we just think of it as 3 going in front and leaving behind 2, and not pondering over all these geometric interpretations and meaning, yeah. Because that's what it's easier.
That's the kind of thing that happens when these tend to fall in the middle of much longer computations. But rather than chucking it all off to symbolic patterns, let's just take a moment and think about why this works for powers beyond just 2 and 3. When you nudge that input x, increasing it slightly
Okay,
to
so I
x
think
plus
now he's gonna give the algebraic proof, some idea of the algebraic proof, how when expanding these things, first of all we have x to the power n, and then n x to the power n minus 1 dx, and then other contains multiples of dx square, yeah. So except the one that contains dx, others will just go to 0, so we will just have n x to the power n minus 1 dx, yeah. I think he will give the algebraic proof now. Think of
plus dx, working out the exact value of that nudged output would involve multiplying together these n separate x plus dx terms. The full expansion would be really complicated, but part of the point of derivatives is that most of that complication can be ignored. The first term in your expansion is x to the n. This is analogous to the area of the original square, or the volume of the original cube from our previous examples. For the next terms in the expansion, you can choose mostly x's with a single dx.
So he's like showing how to multiply as well.
Since there are
That's nice.
n different parentheticals from which you could have chosen that single dx, this gives us n separate terms, all of which include n minus 1 x's times a dx, giving a value of x to the power n minus 1 times dx. This is analogous to how the majority of the new area in the square came from those 2 bars, each with area x times dx, or how the bulk of the new volume in the cube came from those 3 thin squares,
trying to really
each of which had a
simplify it a
volume
lot.
of x squared times dx. There will be many other terms in this expansion, but all of them are just going to be some multiple of dx squared, so we can safely ignore them.
And they will go to
And what
0,
that means is that all but a negligible portion of the increase in the output comes from n copies of this x to the n minus 1 times dx. That's what it means for the derivative of x to the n to be n times x to the n minus 1. And even though, like I said, in practice you'll find yourself performing this derivative quickly and symbolically, imagining the exponent hopping down to the front, every now and then it's nice to just step back and remember why these rules work.
Yeah,
Not
it's
just
really
because it's
helpful,
pretty, and not just
to
because
get with these things.
it helps remind us that math actually makes sense and isn't just a pile of formulas to memorize.
Yeah,
But because it
in
flexes
every
that
formulas, there's an underlying reason. In if you are trying to understand those formulas, it's really like it feels really nice and like interesting. Yeah, to do maths.
very important muscle of thinking about derivatives
It
in
flexes
terms
that
of tiny
really
nudges.
important muscles of thinking about derivatives in terms of time nudges. Yeah.
As another example, think of the function f of x equals 1 divided by x.
Okay.
Now, on the one hand, you could just blindly try applying the power rule, since 1 divided by x is the same as writing x to the negative 1.
Okay, so I've
That would
never heard of any like intuitions for this function, and I think that it's going to be really interesting if it gives us any intuition. Yeah, like till the date, I just used the power rule, and that worked. But now let's see.
involve letting the negative 1 hop down in front, leaving behind one less than
And
itself,
even like,
which is negative.
did I ever prove this thing? Can we do the first principle? Let's try doing this a first principle first of all, and then let's see like if we can do this or not. So limit delta x goes to 0, and then 1 by x plus delta x minus 1 by x by delta x. Now let's see how do we do this. Oh, it's easy, it doesn't take much time. Just take the LCM, x minus delta x by x plus delta x. Okay, it simplifies now. We just get limit delta x tends to 0, so it's minus delta x. Yeah, and that cancels out, so minus 1 by x squared now. If this goes to 0, yeah, it's easy to prove this. But now let's see the intuition behind this.
Negative 2. But let's have some fun and see if we can reason about this geometrically rather than just plugging it through some formula. The value 1 over x is asking what number multiplied by x equals 1. So here's how I'd like to visualize it. Imagine a little rectangular puddle of water sitting in 2 dimensions whose area is 1. And let's say that its width is x.
Okay, so it feels like for a small change in width. Okay, no. For a small change in length, how is width gonna increase? Isn't that the question? Like, I think let's try it first on our own, and then we will watch his video. Okay, because that's interesting. Okay, so now if we think in this way that length x and breadth 1 by x, area is 1. Now to find the derivative of f of x equals to 1 by x, for a small change in x, that means for a small change in L, what is the small change in breadth will be? Okay. Okay, so area will just be 1, and if we have x plus delta x, now we need to find delta b. Yeah, okay, and 1 by x. Okay, wait. But like how do I deal with this? We need to find the change in this. Like all year, what did I do for change find love? But the area isn't changing over here. Yeah. Okay, so what can we do is 1 by x plus delta x. Okay, so this one minus 1 by x. This thing should be equal to 1 by x plus delta x. Yeah. Now, how do I actually find this thing? Okay. That means it decreases by 1 by x square. Okay, so let's see it like this from the. Okay, so basically, this is length x, yeah, and this is 1 by x, yeah. Okay, so now if it has to increase by some length, the height has to decrease, yeah. Okay, now this increase. Okay, so corresponding to this increase, we do have some decrease, and these two are equal, so as to conserve the area to be 1. This is delta x, and this is delta 1 minus 1 by x. Yeah, and now what do we need to find? Now we need to find, like, corresponding to, we need to find the corresponding to a change in x. What is the decrease in delta x? Okay, so we need to find the decrease in delta x. Sorry, decrease in 1 by x, yeah. So basically we need to find this length. Okay, so for finding that length, we first know that this area is delta x times 1 by x. That's why this area will also be delta x times 1 by x. Yeah, and the total length is x. Oh yeah, so that's why now this length will just be total area is delta x times 1 by x divided by the length by x. So this change is just delta x by x square. I proved it. Wow. Yeah, so basically if I take d of 1 by x square, 1 by x, this is just minus 1 by x square times dx. Yeah, and yeah, I did prove it. Okay, so this was a nice proof, like, to think of. Okay, so basically what it did was, for a small decrease in x, there is a certain increase in x, because the whole volume has to be conserved to become 1. And now this area and this area has to be equal. This area is delta x times 1 by x. Yeah, this area should also be same. Now, but since you know the area, we can divide by length to get the breadth. Breadth is delta 1 by x, and yeah, that was a nice one, and I'm really happy to have done. Though it was simple, but I'm happy anyway.
Which means that the height has to be 1 over x, since the total
Anyone there? Fine.
area of it is 1. So if x was stretched out to 2, then that height is forced down to 1/2. And if you increased x up to 3, then the other side has to be squished down to 1/3. This is a nice way to think about the graph of 1 over x, by the way. If you think of this width x of the puddle as being in the xy plane, then that corresponding output.
Okay, so this is the graph of 1 by x, is it? Because we are just plotting 1 by x, yeah.
1 divided by x, the height of the graph above that point, is whatever the height of your puddle has to be to maintain an area of 1.
But this also gives a really nice way to draw. Okay, so, like, I never thought it this way, that this length will just be x, yeah. Okay, area to be 1. So basically this is graph of 1 by x. Okay, so when the height is 1 by x, at that point just replace x to 1 by x, so you get x. Fine.
So with this visual in mind, for the derivative, imagine nudging up that value of x by some tiny amount, some tiny dx. How must the height of this rectangle change so that the area of the puddle remains constant at 1? That
Yeah.
is, increasing the width by dx adds some new area to the right here. So the puddle has to decrease in height by some d1 over x so that the area lost off of that top cancels out the area gained. You should think of that d1 over x as being a negative amount, by the way,
Yeah.
since it's decreasing the height of the rectangle.
Yeah.
And you know what? I'm going to leave the last few steps here for you to pause and ponder and work out an ultimate expression.
Yeah, and we already did that because these two are equal dx times 1 by x times d1 by x. Yeah. So we already did this. Both of these should be equal. So that's why we get dx times 1 by x is equals to d1. Okay, this is bad now. And then d1 by x times x. So you can take x to other side and we get d1 by x. And of course, the dx is negative, yeah, because x. Okay, no, not nothing, not dx is negative. Like what should be negative here to maintain this thing? Dx is also positive. Okay, so basically, how do I maintain negative sign over here? Delta x is positive. It's in fact that. Okay, so how do I maintain this? d1 by x change in 1 by x. Okay, so I think I should put it over here because negative change. Yeah. So minus d1 by x equals to, now that is just dx by x square. This was an easy proof. Yeah. And take the sign over here and you get the proof. Take the sign over there and you can write this as d1 by x by dx is equals to minus 1 by x square. Okay.
And once you reason out what d of 1 over x divided by dx should be, I want you to compare it to what you would have gotten if you had just blindly applied the power rule, purely symbolically, to x to the negative 1. And while I'm encouraging you to pause and ponder, here's another fun challenge if you're feeling up to it.
Okay,
See if
let's try this as well. To find the derivative of square root x. Let's try this. It's going really fun, yeah. So basically, let's try to find the derivative of square root of x using this visual method. Okay, this is square root of x. This is square root of x. Okay, so now in this case, we want to find the change in square root of x when there is change in x. Okay, basically let's say there's a small change in x, the area, but how will you know? Okay, so let's say the small change in the x is our area. The small change in area, let it be in both the sides. Let us do something like this. Okay, now we need to find the change in root x. Okay, yeah, it will of course be in both sides because for because it's a square, yeah, because it's a square, like both of the side needs to change if it needs to change the area. Okay, yeah, now that isn't an assumption anymore, that's reality now. And if there's a small change in area, yeah, now we need to find this area. So now the small change in area is basically these two areas, yeah. This one over here is also what is this thing? Okay, so this over here is del of root x, and this over here is also del of root x, yeah. So del of root x times x plus there also del of root x times x. Like, no, it's not x. Wait a second. So that is this length over here is also root x, yeah. Del of root x times root x, also over here del of root x times root x also. del of root x times root x. Okay, so let me write del over here. Now we have del x as 2 times root x del of root x. So we get that del of root x is actually del x by 2 root x. And yeah, now this is the answer, because we know that derivative of root x is just 1 by 2 root x times dx. Yeah, so we got that result over here. Now we can just take del x to other side, and we get del of root x by del x is equals to 1 by 2 root x. Now I'm really finding all of these proofs really beautiful. Yeah, because even myself, I never did see, though I'm not anything, like, though I'm not any great person, but but like I never did see I never really did see any of these things in such a way. Yeah, geometrically I never really did see this thing. This one was more beautiful even than this. Yeah, because it was the first thing that was out of what I saw. These were already seen. I already seen about this cuboids, but these were new for me, and I really enjoyed like solving this. And thanks Grant Sanderson for this, and let's continue watching his video.
If you can reason through what the derivative of the square root of x should be.
And you can also just use power rule, and you can write this as 1 by 2 x to the power minus 1 by 2. But that does not give any intuition on why this should be true. But this one was so nice. Yeah.
To finish things off,
And now I'll never forget why this was all true. Yeah, this was a beautiful result.
Trigonometric.
I skipped
here of this rect.
Oh,
So
no.
the lost off E1 over and work out an ultimate expression. And once you reason,
So all of those are beautiful. Yeah. First of all, square, and then cube, and then 1 by x, and then square root of x, and the next is sine function, and that's even more beautiful. I will say, because we already proved that, and that
now
was so
what
nice.
d of 1 over x divided by dx should be. I want you to compare it to what you would have gotten if you had just blindly applied the power rule, purely symbolically, to x to the negative 1. And while I'm encouraging you to pause and ponder, here's another fun challenge if you're feeling up to it. See if you can reason through what the derivative of the square root of x should be.
Yeah, we already did that. Yeah.
To finish things off, I want to tackle one more type of function, trigonometric functions. And in particular, let's focus on the sine function. So for this section, I'm going to assume that you're already familiar with how to think about trig functions using the unit circle, the circle with a radius 1 centered at the origin. For a given value of theta, like say 0.8, you imagine yourself walking around the circle starting from the rightmost point until you've traversed that distance of 0.8 in arc length.
Yeah.
This is the same thing as saying that
That is
the
equal
angle
to
right
the-
here
that
is
is in
exactly
radian
theta
measurement.
radians, since the circle has a radius of 1. Then what sine of theta means is the height of that point above the
and the
x-axis.
base is cos theta. Yeah.
And as your theta value increases, and you walk around this circle, your height bobs up and down between negative 1 and 1.
And this is also
So
a
when you
simple harmonic
graph
motion.
sine of
The
theta
height-
versus theta, you get this wave pattern, the quintessential wave pattern. And
Yeah.
just from looking at this graph, we can start to get a feel for the shape of the derivative of the sine. The slope at 0 is something positive, since sine of
But
theta
in
is
this way,
increasing.
the graph doesn't really give an idea of what the slope should be, but changing the idea from the graph to the circle, we can find that. So in math, it's really helpful to change perspective and think about a thing most of the times. Yeah.
There. And as we move to the right and sine of theta approaches its peak, that slope goes down to 0. Then the slope is negative for a little while the sine is decreasing, before coming back up to 0 as the sine graph levels out. And as you continue thinking this through and drawing it out, if you're familiar with the graph of trig functions, you might guess that
No,
this
this is the
derivative
graph of
graph should be
cosine, yeah.
exactly cosine of theta, since all the peaks and valleys line up perfectly with where the peaks and valleys for the cosine function should be. And spoiler alert, the derivative is in fact the cosine of theta.
Spoiler.
But aren't you a little curious about why it's precisely cosine of theta?
Yeah.
I mean, you could have all sorts of functions with peaks and valleys at the
Yeah.
same points that have roughly the same shape. But who knows? Maybe the derivative of sine could have turned out to be some entirely new type of function that just happens to have a similar shape.
Mm.
Well, just like the previous examples, a more
There's a
exact
more
understanding
exact
of the derivative
understanding.
requires looking at what the function actually represents, rather than looking at the
Yeah,
graph.
sine theta represents b by s.
So think back to
p
that
by
walk
s.
around the unit circle.
That will help us.
Having traversed an arc with length theta and thinking about sine of theta as the height of that point. Now,
Now I have come to love the fact that like he is trying to give geometric interpretation to everything, and that's really beautiful. Like sometime before, like I really did think that zeta have to like it won't have any circular meaning in terms of geometry. It's just there, or not just Wallis product, yeah, or the 1 minus 1 by 3 plus 1 by 5, that thing. I never like really believed, even never really believed that those would have a connection with circles or pies. But Grant made me to believe, because there are a lot of videos where he explains these things beautifully, and yeah, they are so nice.
now zoom into that point on the circle and consider a slight nudge of d theta along their circumference, a tiny step in your walk around the unit circle.
Yeah,
How much does that tiny step change the sine of theta?
yeah. And now, since this is theta, this is gonna be 90 minus theta, and this is again theta, 90 minus theta, and this is theta. So now you see that d sine theta by d theta is just cos theta, because that is just b by s. So you see d sine theta by d theta is cos theta. So that's the derivative, and it really makes sense when you have the geometrical interpretation like this. Yeah.
How much does this increased d theta of arc length increase the height above the x-axis? Well, zoomed in close enough, the circle basically looks like a straight line in this neighborhood.
Yeah.
So let's go ahead and think of this right triangle, where the hypotenuse of that right triangle represents the nudge d theta along their circumference. And that left side here represents the change in height, the resulting d sine of theta. Now this tiny triangle is actually similar to this larger triangle here, with the defining angle theta, and whose hypotenuse is the radius of the circle with length 1. Specifically, this little angle right here is precisely equal to theta radians.
Yeah.
Now, think about what the derivative of sine is supposed to mean. It's the ratio between that d sine of theta, the tiny change to the height, divided by d theta, the tiny change to the input.
And like this derivation also helps us understand how this Leibniz definition of derivative is so powerful. Like it was actually the Leibniz who told us that a derivative can also be written as the fraction of the functional value or change in functional value by the input value. Well, yeah. And if we did not have that definition right now, we wouldn't be able to use that interpretation Grant did, because Newton just wrote this like f dash of theta, and this doesn't give any real meaning. But this gives this, and this tells us that it's actually a fraction of infinite decimals. Yeah, and that's why this proof also works. So thanks to Leibniz for this.
Of the function. And from the picture, we can see that that's the ratio between the length of the side adjacent to the angle theta divided by the hypotenuse. Well, let's see. Adjacent divided by hypotenuse, that's exactly what the cosine of theta means. That's the definition of the cosine. Nice. So this gives us two different really nice ways of thinking about how the derivative of sine is cosine. One of them is looking at the graph and getting a loose feel for the shape of things based on thinking about the slope of the sine graph at every single point. And the other is a more precise line of reasoning, looking at the unit circle itself.
Yeah.
For those of you that like to pause and ponder, see if you can try a similar line of reasoning to find what the derivative of the cosine of theta should be.
Yeah, let's do it. Derivative of cosine of theta, yeah. Derivative of cosine of theta. I'm not really sure if I will be able to do that, but let's see. It's just about trying, yeah. So basically there's a circle. Sorry. And like for some angle theta, please note that this theta is in radian, so this arc will also be equal to theta. Now this time our cosine of theta will be this length, yeah. Now when there's a slight increase in theta, sorry, if there's a slight increase in theta, so basically, okay, so now at this point, this is our change in cos theta, yeah, this is our change in cos theta, d cos theta. Okay, so this is our d cos theta. I think it's pretty much same. Now this is our d theta, and this angle is again the theta, yeah. So now we can just see that sine theta is just d cos theta, but wait, because the value of this length is decreasing. Earlier the height was increasing, yeah, but now it's decreasing, so we should write here minus d cos theta, yeah, because that's decreasing. So minus d cos theta by d theta, yeah, because sine theta is opposite over hypotenuse d theta. So you can see that d cos theta by d theta is just minus sine theta, and that's a pretty nice proof, to be honest. Yeah, so these things really help us to see why these are true. Earlier, earlier when like the first time I saw the proof that derivative of sine theta was cos theta was from the Taylor expansion, yeah. Basically sine theta was x minus x cubed by 3 factorial plus x to the power, and this might be a surprise that I did not see it from the first principle, but from the Taylor expansion. that happens when you are just learning random stuffs on YouTube. Okay, so when you are differentiating this, you get cos theta. You basically don't get cos theta directly. You get a new polynomial which is 1 minus, now this is x squared to factorial now, because 3 comes out, 3 comes in the front and cancels, to factorial plus x to the power 5 factorial, yeah. Now this Taylor series is just of cos theta. So that's how I got the idea that derivative of sine is cos. But it did feel like that's a coincidence, and it didn't really give me any intuition. But now, like, it feels so much clear, like why that isn't really any great surprise. Yeah, because why that should just be cos theta. And if you go from the graph, especially from the graph, like it seems like so much of coincidence, because how can the slope of one function just be the graph, yeah, of another? But yeah, like from geometrical, it was nice to see the geometrical interpretations. Yeah. Okay, so 19 viewers have come and gone. Nice.
In the next video, I'll talk about how you can take derivatives of functions who combine simple functions like these ones.
Nice. Now he is going through the rules of derivatives. Yeah, it's nice. We will have product rule, chain rule, cosine rule, power rule. We already did. It's nice to see it.
Either as sums or products or function compositions, things like that. And similar for this.
So this involves chain rule, product rule, and this is just addition rule. Okay. So he will show these things. That's nice.
Video. The goal is going to be to understand each one geometrically in a way that
each
makes
one
it
geometrically, yeah, nice,
and somewhat more memorable.
Okay. Let me drink water again before we start next video. Next is visualizing the chain rule and product rule. Okay.
What exactly is the sandbox then?
It's a 3D metaverse. The building blocks are voxel.
Okay, so I'm excited to visualize chain rules and product rule. Now that we already have some formulas that were calculated through geometric interpretations, Also definition of derivative, that was kind of paradox, and the fundamental theorem of calculus was in the first video. Now this one about the rules. Okay, using chain rule is like peeling an onion. You have to deal with each layer at a time. And if it's too big, you will start crying. Wow, that was so nice. Basically, the last line is so nice. If it's too big, you will start crying because it gets so complicated, and you might not be able to deal with the things. Yeah, and I think the professor is Grant himself. I don't know this, but yeah, this was a really nice quote.
In the last videos, I talked about the derivatives of simple functions. And the goal was to have a clear picture or intuition to hold in your mind that actually explains where these formulas
Basically, we
come
learned about x square, x cube, sin x, cos x, 1 by x, root x. Yeah.
But of course, most of the functions you deal with in modeling the world involve somehow mixing or combining or
Yeah,
tweaking
and
these
in these
simple functions
cases,
in
you
some
need product rule, chain rule, both of them.
other way. So our natural next step is to understand how you take derivatives of more complicated combinations. And again, I don't want these to be something to memorize. I want you to have a clear picture in mind for where each one comes from.
Yeah.
Now, this
And like
really boils
we are
down-
really lucky generations to have such things on the internet easily accessible for us. Yeah, because previous people like might not have got such access, but now we are lucky.
into three basic ways to combine functions. You can add them together,
Add
you
them,
can multiply
multiply,
them,
or
and you can throw one inside the other.
or composing them. Yeah, this is f times z, this is f of z, this is f plus z. These are the only three ways, because division is also multiplication of inverse, and subtraction is also addition of negatives. Yeah, that's why these three are the basic operations. Also, you might have exponentiation, but exponentiation is also composing of, yeah, because f of g, if f is e to the power x and g is 4x, so kind of composing things. Yeah, this cannot be this cannot be told as composing, but this can be told as composing, I guess. Yeah, we can. Let's see.
Known as composing them. Sure, you could say subtracting them, but really that's just multiplying the second by
like how come
negative
our
one.
like thought process be matched? I also thought the same, and he's also thinking the same. That's cool.
And adding them together. And likewise,
Yeah, he also said of division. Nice.
dividing functions doesn't really add anything, because that's
I
the
think
same as
like let's see if he says about exponentiation as composing or not. Let's see.
plugging one inside the function 1 over x, and then multiplying the two together. So really, most functions you come across just involve
He did not say about exponentiation. Fine.
layering together these three different types of combinations, though there's not really a bound on how monstrous things can become. But as long as you know how derivatives play with just those three combination types, you'll always be able to just take it step by step and
So this one is actually not that hard. Just first of all use power rule, and then use product rule, and for both of them use chain rule. Yeah, derivative is not that hard. Integral is hard. If you have to take integral, it will take years. Yeah.
three combination types, you'll always be able to just take it step by step and peel through the layers for any kind of monstrous expression.
Yeah. Yeah.
So the question is, if you know the derivative of two functions, what is the derivative of their sum, of their product, and of the function composition between them? The sum rule is easiest, if somewhat tongue-twisting to say out loud. The derivative of a sum of two functions
Yeah, this one is actual tongue twisting. Derivative of the sum is the sum of the derivative.
is the sum of their derivatives. But it's worth warming up with this example by really thinking through what it means to take a derivative of a sum of two functions. Since the derivative patterns for products and for function composition...
Okay, so this doesn't hold, but why does it hold for addition? Yeah, that's a nice problem. And we can like see that from basic algebra as well. But let me see how does it show it. Basically, from the algebra, like it will not be that hard to see it, because let's say if f is, let's say, let's say g plus s, then our like del f will just be g plus del z. Sorry, not then del f will just be del z plus del s. So it is kind of obvious, because though if f equals to g as, then our del f will just be okay. So we cannot really go this way. I think I'm missing something. I can't really write it this way. It isn't obvious now. Okay, so basically what I can do is f plus del f. I can write this as g plus del g plus h plus del h. Yeah, now g plus h is just f. Yeah, so f plus del g plus del h. So that's why now it becomes obvious that del f should be del g plus del h. But in when it's product, if let's say f is g h, now in this case our del f is, sorry, not del f, again I'm doing mistake. Okay, so basically our f plus del f is just d plus del g times h plus del h. Yeah, and now this is f plus del f equals to g h plus g del h plus del g times h plus del g del h. Yeah, that's why now gh is just f, so f and gh cancel out. You can see that like this isn't really del g times del h. Yeah, this is actually g del h plus del g times h, and this is negligible. So yeah, this is kind of algebraic proof for, but let's see, like he's gonna give us some interesting ideas.
Won't be so straightforward,
Yeah.
and they're going to require this kind of deeper thinking. For example, let's think about this function f of x equals sine of x plus x squared. It's a function where for every input you add together the
Okay,
values.
so now it will be really interesting. But can we see it in terms of slope? Okay, so basically a slope of this, but how? Slope of the whole function. No, I'm not getting an idea right now. Let's see.
Of sine of x and x squared at that point.
Okay. So he's adding both the functions. Now, okay, that means like what he's trying to show is, I think, basically for a point there's some change in width by change in height. Change in width by change in height. So width is not changed, but height has been added. Yeah. So I think his idea is something like this. So let me just copy the figure and let me try to like give my interpretation on his idea, so that it's really nice to think on your own before you watch something. Yeah. So basically, what he wants to say is, this function is basically, x square plus sine x. Yeah, this new function. Now slope over height. For sine x, there's a small change dx in this height. Yeah. For x square, there's also a dx and this new height. Yeah. And now for this thing, both the heights are added. Yeah, y values are added. So the y1 for x sine x and y2 for x square, and this is, let's say, del x. Its slope is basically y1 plus y2 by del x. Yeah, and the individual slopes are just y1. Is that no? Okay, so I think it's not y1 plus y2. It's actually del. I think I got wrong somewhere. Okay, so basically what we can say is, okay, I think this height is actually double of this height. So at the point where both of them meet, so this one is actually double of it, and I think this one is also del y1 plus del y2. Yeah, this does hold true, because like their heights of these two figures at this point is actually the total height, and the change in their heights is also change in the change entire heights of the sum of these two. So yeah, this does hold true, though I may not have been able to explain, but yeah, Grant will explain in a better way. So because this holds true, yeah, we can say that the derivative of the sum is actually the sum of derivatives. You will explain it better way. Let's see this.
For example, let's say at x equals 0.5, the height of the sine graph is given by this vertical bar,
Hmm.
and the height of the x squared parabola is given by this slightly smaller vertical bar.
Yeah.
And their sum is the length you get by just stacking them together.
Yeah. And over here, like the new height will be this height plus this height.
Now, for the derivative, you want to ask what happens as you nudge that input slightly, maybe increasing it up to 0.5 plus dx. The difference in the value of f between those two places is what we call df. And when you picture it like this, I think you'll agree that the total change in the height is whatever the change to the sine graph is, what we might call d sine of x,
Yeah.
plus
And
whatever
what
the
was
change to
in-
x squared
yeah,
is,
I mean the same.
dx squared.
Yeah.
Now, we know that the derivative of sine is cosine. And remember what that means. It means that this little change, d sine of x, is about cosine of x times dx. It's proportional to...
But wait a second. Like, okay. So this is. This one is sine. This one is just small change. But like, how did he know that this thing over here is 0.5 whole square? Just wrote it because I'm not really convinced why he write this as 0.5 square. Or did he just move it somehow? Did he just move it somehow upward? But then, like, how that should be dx square? This was just line, I guess. Fine.
the size of our initial nudge, dx.
If
And
you
the
are convinced
proportionality
with this, you
constant
can also
equal-
go it from first principles. Yeah, and from first principles, like I did also regularly. Uh, that is also nice way to see this one. Yeah.
Equals cosine of whatever input we happen to start at. Likewise, because the derivative of x squared is 2x, the change in the height of the x squared graph is going to be about 2 times x times whatever dx was.
Yeah.
So, rearranging df divided by dx, the ratio of the tiny change to this sum function to the tiny change in x that caused it, is indeed cosine of x plus 2x,
Yeah.
the sum of the derivatives of its parts.
Yeah.
But like I said, things are a bit different for products. And let's think through why. And let's think through why in terms of tiny nudges again. In this case, I don't think graphs are our
okay.
best bet for visualizing things.
Okay, yeah.
Pretty
But
commonly in
these
math, at a
graphs
lot of
are not
levels
the
of math,
best way.
really.
Like algebra would have been the best way for no having intuition of these rules. Yeah.
If you're dealing with a product of two things, it helps to understand it as some kind of area. In this case, maybe you try to configure some mental setup of a box where the
Okay,
side
box would
lengths
also
are
be
sine of
helpful,
x
but
and
graph
x
was
squared.
not.
But what would that mean? Well, since these are functions, you might think of
Okay,
those
so
sides as
let's try seeing the other ideas using box. Okay, but how do we see it using box? I don't think we will really be able to. Let's say, the total length is this is f and this is g. The addition is, let's say, adds. This one is f, this one is g. Now change in adds is change in some change in f plus some change in g. So del h equals del f plus del g. That is pretty straightforward. But okay, let's go to the video. Oh, how come I end it?
aside. I mean, this whole setup is our sine of x and x squared. They're a bit different for products. And let's think through why. And let's think through why in terms of tiny nudges again. In this case, I don't think graphs are our best bet for visualizing things. Pretty commonly in math, at a lot of levels of math really, if you're dealing with a product of two things, it helps to understand it as some kind of area.
Yeah.
In this case, maybe you try to configure some mental setup of a box where the side lengths are sine of x and x squared. But what would that mean? Well, since these are functions, you might think of those sides as adjustable, dependent on the value of x, which maybe you think of as this number that you can just freely adjust up and down.
Yes, before we see this beautiful proof, I want to go to restroom again. Yeah, and pardon me for that. Okay, so I'm back and I will have some water and then let's go through this.
So getting a feel for what this means, focus on that top side there, who changes as the function sine of x. As you change this value of x up from 0, it increases up to a length of 1 as sine of x moves up towards its peak. And after that, it starts to decrease as sine of x comes down from 1. And in the same way, that height there is always changing as x squared. So f of x, defined as the
So
product of these two
basically,
functions,
height was
is going to be
increasing and
the
sine x
area of this
decreases.
box. And for the derivative, let's think about how a tiny change to x by dx influences that area. What is that resulting change in area df? Well, the nudge dx caused that width to change by some small d sine of x, and it caused that height to change by some dx squared.
Okay, so basically, okay, so both the sine x and x square are changing. Yeah, okay, fine. So there are two changes over here. I think this is the same as I did in algebraically. D sine x times x square plus dx square times sine x. Fine.
And this gives us three little snippets of new area. A thin rectangle on the bottom, whose area is its width, sine of x, times its thin height, dx squared. And there's this thin rectangle on the right, whose area is its height, x squared, times its thin little width, d sine of x. And there's also this little bit in the corner, but we can ignore that. Its area is ultimately going to be proportional.
We can ignore that. It's like some small people getting ignored. Yeah, fine.
To dx squared, and as we've seen before, that becomes negligible as dx goes to 0.
Yeah.
I mean, this whole setup is very similar to what I showed last video with the x squared diagram. And just like then, keep in mind that I'm using somewhat
I did tell that in the last video that that was similar to product rule, and now it's becoming obvious to you as well.
changes here to draw things, just so that we can actually see them. But in principle, dx is something very, very small, and that means that dx squared and d sine of x are also very, very small. So, applying what we know about the derivative of sine and of x squared, that tiny change, dx squared, is going to be about 2x times dx. And that tiny change d sine of x, well, that's going to be about cosine of x
dx.
times dx. As usual, we divide out by that dx to see that the ratio we want, df divided by dx, is sine of x times the derivative of x squared, plus x squared times the derivative of sine.
Mm.
And nothing we've done here is specific to sine or to x squared. This same line of reasoning would work for any two functions, g and h.
Yeah.
And sometimes
it
people like to
makes
remember this
sense,
pattern with
just
a
remember
certain
the
mnemonic that you kind of sing in your
Okay,
head.
yeah. So this is the
Left,
formula: left, d right plus right, d left. And if there are three functions, let me just tell you now, because it can be helpful for you sometimes. And if there were three functions instead of just two functions, let's say f equals to g as m n for function, then f dash. Okay, so then df by dt, this would be, first of all, differentiate g, dg by dt, and others as it is, h m n plus, now differentiate as g times ds by dt, others as it is, m n, now differentiate m, dm by dt, and n as it is, plus then ghm, differentiate n, dn by dt. Okay, so this is the general product rule for others. You can derive this in similar fashion. Basically, if you take like 3 into 3 box instead of a rectangle, you can see that just like previously, 3 snippets will remain where one of them would have 2 lengths and 1 differential, 2 lengths and differential. You can derive this in the similar fashion. Yeah.
Right, right, d left. In this example, where we have sine of x times x squared, left d right means you take that left function, sine of x, times the derivative of the right, in this case 2x.
Yeah.
Then you
And
add
like
on
I
right
really
d
like
left.
how these pies are seeing these things in such a curious manner. Yeah.
That right function, x squared, times the derivative of the left
And
one,
those are really
cosine of
learning.
x. Now, out of context, presented as a rule to remember, I think this would feel pretty strange, don't you?
I think
But-
this one is the Grant and these are the learners, I guess.
When you actually think of this adjustable box, you can see what each of those terms represents.
Yeah.
Lefty right is the area of that little bottom rectangle,
Mhm.
and right d left is the area of that rectangle on the side.
Yeah.
By the way, I should mention that if you multiply by a constant, say 2 times sine of x, things end up a lot simpler. The derivative is just the same as the constant multiplied by the derivative of the function. In this case,
You can also
2 times...
prove this from product rule because okay, so if you want to prove this from product rule, it's really easy because some of you might not be convinced how can constant taken out in. For that, you can just use product rule, and that will help you get convinced. So you can basically take 2 and then derivative of this is cos x plus derivative of 2 is 0 and then this is sin x. Yeah, so you see this cancels out, so you just have 2 times cos x. This is same as constant getting taken out. You can prove that this for k times fx as well, and you see that its derivative is just k times f plus x from the product rule itself, and that can help you get convinced. Yeah.
times cosine of x. I'll leave it to you to pause and ponder and just kind of verify that that makes sense.
Yeah.
Aside from addition and multiplication, the other common way to combine functions, and believe me, this one comes up all the time, is to shove one inside the other. Function
Yeah.
composition.
Yeah.
For example, maybe we take the function x
Let's try to
squared.
prove this ourselves directly. Yeah, I've not really done this. I don't know, like, but I don't really remember doing this or proving this. Let's say h of x is f of g of x. If you want to, okay, so now h plus delta h, this is, okay, so this is f of g of x plus delta x minus f of g of x. Now I do think this is standard approach. Like I can Okay, so I think okay. So this is just delta s, not s plus delta s, because I have differentiated. Now I think I'm gonna go with the first principle itself, because now I can divide this by g of x plus delta x minus g of x. Again, write that over here. But this doesn't give us any intuition. Just that it gives us the idea that it is true. But intuitional understanding, this does lack. Yeah. So I think Grant will help us to get the idea. Now this is just f dash of g of x, and this is g dash of x. So for intuition, let's watch his videos now. Oh, why does it
Number
that?
lines. Aside from addition and multiplication, the other common way to combine functions, and believe me, this one comes up all the time,
Yeah.
is to shove one inside the other, function composition. For example, maybe we take the function x squared and we just shove it on inside sine of x to get this new function sine of x squared.
Yeah.
What do you think the derivative of that new function is? To think this one through, I'm going to choose yet another way to visualize things, just to emphasize that in
I
creative
think
math,
this
we've
is
got
gonna
lots
be
of options.
interesting, because I have also never heard of this. So I think I'm gonna enjoy this.
I'll put up 3 different number lines. The top one is going to hold the value of x, the second one is going to hold the value of x squared, and that third line is going to hold the value of sine of x squared. That is, the function x squared gets you from line 1 to line 2, and the function sine gets you from line 2 to line 3. As I shift around this value of x, maybe moving it up to the value 3, that second value stays pegged to whatever x squared is, in this case moving up to 9. And that bottom value, being sine of x squared, is going to go to whatever sine of 9 happens to be. So for the derivative, let's again start by just nudging that x value by some little dx. And I always think that it's helpful to think of x as starting at some actual concrete number, maybe 1.5 in this case. The resulting nudge to that second value, the change in x squared caused by such a dx, is dx squared. And we could expand this like we have before as 2x times dx, which for our specific input would be 2 times 1.5 times dx, but it actually helps to keep things written as dx squared, at least for now. And in fact, I'm going to go one step further. I'm going to give a new name to this x squared, maybe h, so that instead of writing dx squared for this nudge, we write dh. And this makes it easier to think about that third value, which is now pegged at sine of h. Its change is d sine of h, the tiny change caused by the
Basically
nudge.
just the other way around of the same proof. Yeah, basically in this proof as well, we basically try to look g x plus delta x as y plus delta y minus y. So we just renamed this variable as y plus delta y, and then did the same stuff. Yeah, basically that proof also seems the same. Yeah, so I'm not really feeling anything special. Yeah, well, let's see, but it's a nice way to see things than how I showed you. But yeah,
dh. And by the way, the fact that it's moving to the left while the dh bump is going to the right, that just means that this change, d sine of h, is going to be some kind of negative number. And once again, we can use our knowledge of the derivative of the sine. This d sine of h is going to be about cosine of h times dh. That's what it means for the derivative of sine to be cosine.
nice.
And
So okay, that's nice. But the fact that we can substitute x as x square. But why does this proof sound circular to me? But I don't think this needs any proof, by the way. Like basically, like, I don't really think this needs any proof. The reason is basically, if you want to find d sine of x square, basically with respect to, let's say, dx, yeah, what you can do is we can just write dx square over here, and then dx squared by x dx. Yeah. Now he's just saying like we replace this by as, and why replace, because we can compare it in as it is as well. Sin as dx, so this is cos x squared to x dx. So I don't think this was any kind of proof, but and it needs any proof because that's just obvious. Okay, right.
Unfolding things, we can just replace that h with x squared again. So we know that that bottom nudge is going to have a size of cosine of x squared times dx squared. And in fact, let's unfold things even further. That intermediate nudge dx squared is going to be about 2x times dx. And it's always a good habit to remind yourself of what an expression like this actually means. In this case, where we started at x equals 1.5 up top, this whole expression is telling us that the size of the nudge on that third line is going to be about cosine of 1.5 squared times 2 times 1.5 times whatever the size of dx was. It's proportional to the size of dx, and this derivative is giving us that proportionality constant.
Basically, it's multiplied by the nudge over here as well. Okay, fine.
Notice what we came out with here. We have the derivative of the outside function, and it's still taking in the unaltered inside function, and then we're multiplying it by the derivative of that inside function.
Yeah.
Again, there is nothing special about sine of x or x squared. If you have any two functions, g of x and h of x, the derivative of their composition, g of h of x, is going to be the derivative of g evaluated on h, multiplied by the derivative of h.
Yeah.
This pattern right here is what we usually call the chain rule.
Yeah, chain rule.
Notice, for the derivative of g, I'm writing it as dg
So guys, this is the proof of chain rule. Yeah.
h instead of dg dx. On the symbolic level, this is a reminder that the thing you plug into that derivative is still going to be that intermediary.
Yeah, so this is the main point. If there's as, and if you can write over here just d as, then this is just as dash, nothing more. Okay. No, sorry, g dash of as. Yeah. Basically, this was the trick in driving this formula.
Function h. But more than that, it's an important reflection of what this derivative of the outer function actually represents. Remember, in our three-line setup, when we took the derivative of the sine on that bottom, we expanded derivative of the outer.
Oh, is this product of derivative and as? Oh, so I basically told wrong thing. This is derivative of g and then as
function
as
actually
function.
represents. Remember, in our three-line setup, when we took the derivative of the sine on that bottom, we expanded the size of that nudge, d sine, as cosine of h times dh. This was because we didn't immediately know how the size of that bottom nudge depended on x. That's kind of the whole thing we were trying to figure out.
Yeah.
But we could take the derivative with respect to that intermediate variable, h.
And that was the powerful
figure out
part.
how to express the size of that nudge on the third line as some multiple of dh, the size of the nudge on the second line. And it was only after that that we unfolded further by figuring out what dh was.
Yeah.
So in this chain rule expression, we're saying, look at the ratio between a tiny change in g, the final output, to a tiny change in h that caused it.
And
H
over
being
here
the
also,
value that we plug into
the
g.
fractional representation where d as can cancel out. Yeah, that also helps just to understand, just to have like an intuition or better understanding, something like that.
Then multiply that by the tiny change in h divided by the tiny change in x that caused it. So notice, those dh's cancel out, and they give us a ratio between the change in that final output and the change to the input that, through a certain chain of events, brought it about. And that cancellation of dh is not just a notational trick. That is a genuine reflection of what's going on with the tiny nudges that underpin everything we do with derivatives. So those are the three basic tools to have in your belt to handle derivatives of functions that combine a lot of smaller things. You've got the sum rule, the product rule, and the chain rule. And I'll be honest with you, there is a big difference between knowing what the chain rule is and what the product rule is, and actually being fluent with applying them in even the most hairy of
Yeah,
situations.
there's a big difference.
Watching videos, any videos, about the mechanics of calculus is never going to substitute for
Yeah,
practicing
yeah,
those
just
mechanics.
yeah. I was thinking the same. Like just knowing the logics behind these are the proofs are some of the coolest proofs of why this work. These are only going to give you the idea of like why this works and like what's the reason. But like doing maths is way more than just understanding. Yeah, you have to be fluent with that as well. You have to solve a lot of problems, be adapted with solving these problems. Yeah, and only having the like, powerful ideas isn't enough. You have to be a powerful calculator as well. Yeah.
Mechanics yourself, and building up the muscles to do these computations yourself.
Yeah.
I really wish that I could offer to do that for you, but I'm afraid the ball is in your court, my friend, to seek out the practice.
Yeah.
What I can offer, and what I hope I have offered, is to show you where these rules actually come from. To show that they're not just something to be memorized and hammered away.
Yeah, and this is also the reason why Asians are good at maths because they do a lot of homeworks.
But they're natural patterns, things that you too could have discovered just by patiently thinking through what a derivative actually means.
Yeah. Okay, so our next video is what's so special about the very last number E. Okay, this video looks so cool to me. And again, because I'm drinking a lot of water, like I have to go restroom a lot of times, and I'm again going now. Fine, and we'll watch this amazing video after that. Okay, I'm back. And let me tell you that I was also curious from the beginning about how is he going to introduce E. Because since now he never introduced e to the power x with us and just dealt with other functions for telling us about all these tools. Yeah, but E comes everywhere, and most of the time in high school we are introduced this as a number, and e to the power x is e to the power x, and that's the definition of it, and it goes on that way. And that's why like it's really necessary and like somehow tedious and difficult to introduce E in high school, and just they let us just to know that this is a number and derivative is itself and nothing more than that. So let's see how does he introduce us to E. After this we do have a lot of other things, but let's not reveal that now because that will be a spoiler. Okay, I think this is also from unknown. Is that? Oh, Francis Leon, nice. Who has not been amazed to learn that the function y equals e to the power x, like a phoenix rising again from its own ashes, is its own derivative. Wow, nice.
I've introduced a few derivative formulas, but a really important one that I left out was exponentials. So
Yeah.
here, I want to talk about the derivatives of functions like 2 to the x, 7 to the x, and also to show why e to the x is arguably the most important of the exponentials.
Yeah.
First of all, to get an intuition, let's just focus on the function 2 to the x. And let's think of that input as a time, t, maybe in days, and the output, 2 to the t, as a population size, perhaps of a particularly fertile band of pie creatures, which doubles every single day. And actually, instead of population size, which grows in discrete little jumps with each new baby pie creature, maybe let's think of 2 to the t as the total mass of the population. I think that better reflects the continuity of this function, don't you? So,
Yeah.
for example, at time
It
t
means
equals
that
0,
number is discrete, but mass can be continuous. Yeah.
the total mass is 2 to the 0 equals 1 for the mass of one creature. At t equals 1 day, the population has grown to 2 to the 1 equals 2 creature masses. At day t equals 2, it's t squared, or 4, and in general, it just keeps doubling every day. For the derivative, we want dm dt, the rate at which this population mass is growing,
Yeah.
thought of as a tiny change in the mass divided by a
So,
tiny change in time.
Yeah.
And let's start by thinking of the rate of change over a full day, say between day 3 and day 4. Well, in this case, it grows from 8 to 16, so that's 8 new creature masses added over the course of one day.
Yeah.
And notice, that rate of growth equals the population size at the start of the day. Between day 4 and day 5, it grows from 16 to 32, so that's a rate of 16 new creature masses per day, which again equals the population size at the start of the day. And in general, this rate of growth,
the number by which it increases in one day is actually equal to the number that we had in the beginning of the day. So that's an interesting observation that he makes.
growth over a full day equals the population size at the start of that day.
Oh yeah, nice
So it
observation.
might be
That means
tempting to say that
that means like what he means to say is, and this is also a nice thing in discrete calculus. So basically, in discrete calculus, yeah, I don't know the symbol for derivative in discrete calculus though, but in discrete calculus, derivative of 2 to the power t is just 2 to the power t. Yeah, and that is what he means right now, because in discrete calculus the change happens by a 1 to any integer numbers, basically by 1. Yeah, so basically if initially we had, let's say, 2 to the power 5, yeah, and this doubles, so it increases by 2 to the power 5 again. So basically he's trying to show that derivative of 2 to the power t is just itself in discrete calculus, and that's a pretty nice observation, to be honest.
this means the derivative of 2 to the t equals itself. That the rate of change
But
of this
not in
function at a
continuous,
given
because
time t
we are just
is
seeing
equal
it
to,
for one
well,
day,
the
not
value
for
of
1
that
second.
function. And this is definitely in the right direction, but it's not quite correct.
Yeah.
What we're doing here is making comparisons
Yeah,
over a full
yeah.
day, considering the difference between 2 to the t plus 1
Okay, so
and 2 to the
instead
t.
of 1 and 1 over here, we need to have delta t or delta t over here. This is only done in discrete calculus, and this is true. Yeah.
But for the derivative, we need to ask what happens for smaller and smaller changes.
Yeah.
What's the growth over the course of a tenth of a day, a hundredth of a day, 1/1 billionth of a day? This is why I had us
Yeah.
think of the function as representing population mass, since it makes sense to ask about a tiny change in mass over a tiny fraction of a day,
Yeah.
but it doesn't make as much sense to ask about the tiny change in a discrete population size per. More abstractly, for a tiny change in time, dt, we want to understand the difference between 2 to the t plus dt and 2
Yeah,
to the t,
exactly.
all divided by dt. The change in the function per unit time, but now we're looking very narrowly around a given point in time rather than over the course of a full day. And here's the thing. I would love if there was some very clear geometric picture that made everything that's about to follow just pop out. some diagram where you could point to one value and say, see, that part, that is the derivative of 2 to the t. And if you know of one, please let me know. And while the goal here, as with the rest of the series, is to maintain a playful spirit of discovery, the type of play that follows will have more to do with finding numerical patterns rather than visual ones. So start by just taking a very close look at this term, 2 to the t plus dt. A core property of exponentials is that you can break this up as 2 to the t times 2 to the dt.
I think that he will take 2 to the power t common and use some very small dt and find the remaining value, and that is almost equals to ln of t, yeah. And he's gonna raise that to the power of e, and that comes 2. And for 3, that comes 3. Something like that. I don't know.
That really is the most important property of exponents. If you add two values in that exponent, you can break up the output as a product of some kind.
If that pattern
This
is
is
the
what-
case over here, observing that is really difficult, I guess.
Lets you relate additive ideas, things like tiny steps in time, to multiplicative ideas, things like rates and ratios.
Okay.
I mean, just look at what happens here. After that move, we can factor out the term 2 to the t, which is now just multiplied by 2 to the dt
Just a second.
minus 1, all divided by dt. And remember, the derivative of 2 to the t is whatever this whole expression approaches as dt approaches 0. And at first glance, that might seem like an unimportant manipulation. But a tremendously important fact is that this term on the right, where all of the dt stuff lives, is completely separate from the... It doesn't depend on the actual time where we started.
Okay, so
You can go off to a calculator and plug in very small values for dt here. For example, maybe typing in 2 to the 0.001 minus 1 divided by 0.001. What you'll find is that for smaller and smaller choices of dt, this value approaches a very specific number, around 0.6931. Don't worry if that number seems mysterious. The central point is that this is some kind of constant. Unlike derivatives of other functions, all of the stuff that depends on dt is separate from the value of t itself. So the derivative of 2 to the t is just itself,
it's
but multiplied by some
that
constant.
depend on t.
And that should kind of make sense, because earlier it felt like the derivative for 2 to the t should be itself, at least when we were looking at changes over the course of a full day. And evidently, the rate of change for this function over much smaller time scales is not quite equal to itself, but it's proportional to itself, with this very peculiar proportionality constant of 0.6931.
Okay.
And there's not too much special about the number 2 here. If instead we had dealt with the function 3 to the t, the exponential property would also have led us to the conclusion that the derivative of 3 to the t is proportional to itself. But this time it would have had a proportionality constant 1.0986. And for other bases to your
I'm
exponent,
pretty sure that he is gonna raise this number to powers of e. But how the on or someone will think of doing that? That's my question.
you can have fun trying to see what the various proportionality constants are, maybe seeing if you can find a pattern in them. For example, if you plug in 8 to the power of a very tiny number, minus 1, and divide by that same tiny number, what you'd find is that the relevant proportionality constant
Now for
is around
this, going with algebra is the best, because I don't really think it's possible to find patterns in this way with the algebra. Yeah, just what you can do is, what is the best way for this is this thing. So basically, if you have to take limit dt equals to 0, 2 to the power dt minus 1 dt, we have this, yeah. What you could instead do is limit dt equals to 0. You can use this the property of e to the power log. You get e to the power dt ln of 2 minus 1 by dt ln of 2, and then introduce ln of 2 is 2 over here. Now let dt ln of 2 go to 0. Now this by the property of limit of e to the power x minus 1 by x goes to 1, 8 x equals to x goes to 0. That's why 1 times sine of 2. This would be quite easier than to notice a pattern, I guess, for this one.
0.079. And maybe, just maybe, you would notice that this number happens to be exactly 3 times the constant associated
Oh.
with the base for 2.
But, okay. But this is also based on the property of logarithms that this works. Yeah, this actually works, but observing this, would that be easier? So basically log of 8 is 3 times log of 2. I do agree with yeah, that should work, but maybe somehow this is possible to observe this. Yeah.
So these numbers certainly aren't random. There is
Yeah.
some kind of pattern.
Yeah.
But what is it? What does
Now,
2
since
have to do with the number
exponentials are
0.693?
getting multiplied, it's now somewhat obvious that it should be logarithms. Yeah.
1. And what does 8 have to do with the number 2.079? Well, a second question that is ultimately going to explain these mystery constants is whether there's some base where that proportionality constant is 1, where the derivative of a to the power t is not just proportional to itself, but actually equal to itself. And there is. It's the special constant e, around 2.71828.
But how will someone know
In
this?
fact, it's not just that the number e happens to show up here. This is, in a sense, what defines the number e. If you ask, why does e of all numbers have this property, it's a little like asking, why does pi of all numbers happen to be the ratio of the circumference of a circle? This is, at its heart, what defines this value. All exponential functions are proportional to their own derivative, but e alone is the special number so that that proportionality constant is 1, meaning
so
e to
now,
the t
now you say that's the definition. Nice, fine.
e actually equals its own derivative. One way to think of that is that if you look at the graph of e to the t, it has the peculiar property that the slope of a tangent line to any point on this graph equals the height of that point
Equals the height,
above the
that's the
horizontal
value itself,
axis. The existence of a function like this answers the question of the mystery constants, and it's because it gives a different way to think about functions that are proportional to their own derivative. The key is to use the chain rule. For example, what is the derivative of e to the 3t? Well, you take the derivative of the outermost function, which due to this special nature of e is just itself, and then multiply by the derivative of that inner function, 3t, which is the constant, 3. Or rather than just applying a rule blindly, you could take this moment to practice the intuition for the chain rule that I talked through last video, thinking about how a slight nudge to t changes the value of 3t, and how that intermediate change nudges the final value of e to the 3t.
Yeah.
Either way, the point is, e to the power of some constant times t is equal to that same constant times itself. And from here, the question of those mystery constants really just comes down to a certain algebraic manipulation. The number 2 can also be written as e to the natural log of 2. There's nothing fancy here. This is just the definition of the natural log. It asks the question, e to the what equals 2? So, the function 2 to the t is the same as the function e to the power of the natural log of 2 times t. And from what we just saw, combining the facts that e to the t is its own derivative with the chain rule, the derivative of this function is proportional to itself, with a proportionality constant equal to the natural log of 2. And indeed, if you go plug in the natural log of 2 to a calculator, you'll find that it's 0.6931,
Okay.
the mystery constant that we ran into earlier. And the same goes for all of the other bases. The mystery proportionality constant that pops up when taking derivatives is just the natural log of the base, the answer to the question, e to the what equals that base.
Okay.
In fact, throughout applications of calculus, you rarely see exponentials written as some base to a power t. Instead, you almost always write the exponential as e to the power of some constant times t. It's all equivalent. I mean, any function like 2 to the t or 3 to the t can also be written as e to some constant times t. At the risk of staying over-focused on the symbols here, I really want to emphasize that there are many, many ways to write down any particular exponential function. And when you see something written as e to some constant times t, that's a choice that we make to write it that way. And the number e is not fundamental to that function itself.
Yeah, okay.
What is special about writing exponentials in terms of e like this is that it gives that constant in the exponent a nice, readable meaning. Here, let me show you what I mean.
Yes.
All sorts of natural phenomena involve some rate of change that's proportional to the thing that's changing. For example, the rate of growth of a population actually does tend to be proportional to the size of the population itself, assuming there isn't some limited resource slowing things down. And if you put a cup of hot water in a cool room,
Oh yeah, this
the
is
rate at which the water
Newton's law of
cools,
cooling. Yeah, this says that the drop of temperature is proportional to. Hmm. Why is he keeping delta T over here? You could just keep T instead of delta T. Like drop of temperature, but it is proportional to the temperature that we have right now. So you can remove the delta over here. I don't see the meaning. I think from that delta he means to say the temperature at a point, because temperature is also changing. Yeah, delta T might be the temperature at certain time. And yeah, I think this also makes sense. Fine.
is proportional to the difference in temperature between the room and the
Oh,
water.
delta T means the difference in temperature. Okay, fine. Fine.
Or, said a little differently, the rate at which that difference changes is proportional to itself.
Yeah.
If you invest your money, the rate at which it grows is proportional to the amount of money there at any time.
Yeah.
In all of these cases, where some variable's rate of change
Basically, 1m plus rm, where rm is the new interest. Yeah.
is proportional to itself, the function describing that variable over time is going to look like some kind of exponential. And even though there are lots of ways to write any exponential function, it's very natural to choose to express these functions as e to the power of some constant times t,
Yeah.
since that constant carries a very natural meaning. It's the same as the proportionality constant between the size of the changing variable and the rate of change. And as always, I want to thank those who've made this
Wow.
series possible.
I didn't realize this video finished too fast. Oh, it was shorter as well. Others were of 20, 17. This was 13. Okay. I think next video is gonna be interesting because it's about implicit differentiation. And are these gamma functions? I don't know. Maybe not. Okay. So before we go to the next interesting video on implicit differentiation, let me go to restroom again. There are some pretty interesting names. Justin Helms, Derek Dye. Okay. Now let's go to next video. Haha, the pie. This is really cute one. Let me drink water. Okay, implicit differentiation. What's going on here? Chapter 6, Essence of Calculus. Do not ask whether a statement is true until you know what it means. Yes, like that one is a really good quotation, and which I also support, because some people are just wanting to know what the answer is without knowing what that means in the first place. That's a really nice quotation, in fact.
Let me share with you something that I found particularly weird when I was a student first learning calculus. Let's say that you have a circle with radius 5 centered at the origin of the xy plane. This is something defined with the equation x squared plus y squared equals 5 squared. That is, all of the points on the circle are a distance 5 from the origin as encapsulated by the Pythagorean theorem, where the sum of the squares of the two legs on this triangle equal the square of the hypotenuse, 5 squared. And suppose that you want to find the slope of a tangent line to the circle, maybe at the point xy equals 3, 4. Now, if you're savvy with geometry, you might already know that this tangent line is perpendicular to the radius touching it at that point. But let's say you don't already know that. Or maybe you want a technique that generalizes to curves other than just circles. As with other problems about the slopes of tangent lines to curves, the key thought here is to zoom in close enough that the curve basically looks just like its own tangent line, and then ask about a tiny step along that curve.
Yeah.
The y component of that little step is what you might call dy, and the x component is a little dx. So the slope that we want is the rise over run, dy divided by dx. But unlike other tangent slope problems in calculus, this curve is not the graph of a function. So we can't just take a simple derivative, asking about the size of some tiny nudge to the output of a function caused by some tiny nudge to the input.
Basically, like this is not too hard as well, because we can just differentiate both the sides and use chain rule over here. Okay, so basically, why differentiate both the sides? Maybe that's the question.
An input, and y is not an output. They're both just interdependent values related by some equation. This is what's called an implicit curve.
Implicit curve.
It's just the set of all points, x, y, that satisfy some property written in terms of the two variables, x and y. The procedure for how you actually find dy dx for curves like this is the thing that I found very weird as a calculus student. You take the derivative of both sides like this. For x squared, you write 2x times dx, and similarly y squared becomes 2y times dy. And then the derivative of that constant 5 squared on the right is just 0. Now, you can see why this feels a little strange, right? What does it mean to take the derivative of an expression that has multiple variables in it? And why is it that we're tacking on the little dy and the little dx in this way? But if you just blindly move forward with what you get, you can rearrange this equation and find an expression for dy divided by dx, which in this case comes out to be negative x divided by y. So, at the point with coordinates xy equals 3, 4, that slope would be negative 3 divided by 4, evidently. This strange process is called implicit differentiation. And don't worry, I have an explanation for how you can interpret taking a derivative of an expression with two variables like this. But first, I want to set aside this particular problem and show how it's connected to a different type of calculus problem, something called a related rates problem. Imagine a 5-meter long ladder held up against a wall where the top of the ladder starts 4 meters above the ground, which by the Pythagorean theorem means that that bottom is 3 meters away from the wall. And let's say it's slipping down in such a way that the top of the ladder is dropping at a rate of 1 meter per second. The question is, in that initial moment, what's the rate at which the bottom of the ladder is moving away from the wall? It's interesting, right? That
Yes.
distance from the bottom of the ladder
Can
to the
use
wall
implicit
is
differentiation.
100% determined by the distance from the top of the ladder to the floor. So we should have enough information to figure out how the rates of change for each of those values actually depend on each other. But it might
Yeah.
not be entirely clear how exactly you relate those two.
Yes.
First things first, it's always nice to give names to the quantities that we care about. So let's label that distance from the top of the ladder to the ground y of t, written as a function of time because it's changing. Likewise, label the distance between the bottom of the ladder and the wall x of t.
Yes.
The key equation that relates these terms is the Pythagorean theorem. X of t squared plus y of t squared equals 5 squared.
Yes. Yes.
What makes that a powerful equation to use is that it's true at all points of time.
Yes.
Now, one way that you could solve this would be to isolate x of t, and then you figure out what y of t has to be based on that 1 meter per second drop rate, and you could take the derivative of the resulting function, dx dt, the rate at which x is changing with respect to time.
Yeah, we can do that.
And that's fine. It involves a couple layers of using the chain rule,
Chain rule.
and it'll definitely work for you. But I want to show a different way that you can think about the same problem. This left-hand side of the equation is a function of time, right?
Yeah.
It just so happens to equal a constant, meaning the value evidently doesn't
Oh.
change while
So you are gonna differentiate that with respect to time, yeah? Is it?
time passes, but it's still written as an expression dependent on time, which means we can manipulate it like any other function that has t as an input. In particular, we can take a derivative of this left-hand side, which is a way of saying, if I let a little bit of time pass, some small dt, which causes y to slightly decrease and x to slightly increase, how much does this expression change? On the one hand, we know that that derivative should be 0, since the expression is a constant, and constants don't care about your tiny nudges in time, they just remain unchanged. But on the other hand, what do you get when you compute this derivative? Well, the derivative of x of t squared is 2 times x of t times the derivative of x. That's the chain rule that I talked about last video. 2x dx represents the size of a change to x squared caused by some change to x, and then we're dividing out by dt. Likewise, the rate at which y of t squared is changing is 2 times y of t times the derivative of y.
Okay.
Now, evidently, this whole expression must be 0. And that's an equivalent way of saying that x squared
Okay,
plus y
that
squared
was a nice
must not
trick, by
change
the
while
way.
the ladder moves. At the very start, time t equals 0, the height y of t is 4 meters, and that distance x of t is 3 meters. And since the top of the ladder is dropping at a rate of 1 meter per second, that derivative, dy dt, is negative 1 meters per second. Now, this gives us enough information to...
Whoa. That was pretty nice. Okay. Nice.
isolate the derivative, dx dt. And when you work it out, it comes out to be 4/3 meters per second. The reason I bring up
That is
this
pretty nice, yeah. Yeah.
ladder problem is that I want you to compare it to the problem of finding the slope of a tangent line to the circle. In both cases, we had the equation x squared plus y squared equals 5 squared. And in both cases, we ended up taking the derivative of each side of this expression. But for the latter question, these expressions were functions of time, so taking the derivative has a clear meaning. It's the rate at which the expression changes as time changes. But what makes the circle situation strange is that rather than saying that a small amount of time dt has passed, which causes x and y to change, the derivative just has these tiny nudges dx and dy just floating free, not tied to some other common variable, like time. Let me show you a nice way to think about this. Let's give this expression x squared plus y squared a name, maybe s. S is essentially a function of two variables. It takes every point xy on the plane and associates it with a number. For points on the circle, that number happens to be 25. If you stepped off the circle away from the center, that value would be bigger. For other points xy closer to the origin, that value would be smaller. Now, what it means to take a derivative of this expression, a derivative of s, is to consider a tiny change to both of these variables, some tiny change dx to x and some tiny change dy to y. And not necessarily one that keeps you on the circle, by the way. It's just any tiny step in any direction of the xy plane. And from there, you ask, how much does the value of s change? And that difference, the difference in the value of s before the nudge and after the nudge, is what I'm writing as ds. For example,
Okay. Okay, so basically he's like trying to say that these are the nudges. Fine, fine.
in this picture, we're starting off at a point where x equals 3 and where y equals 4. And let's just say that that step I drew has dx at negative
Okay,
0.02
and
and
if
dy
it has to lie in the same line of 25, not should be 0, yeah.
at negative 0.01, then the decrease in s, the amount that x squared plus y squared changes over that step, would be about 2 times 3 times negative 0.02 plus 2 times 4 times negative 0.01. That's what this derivative expression, 2x dx plus 2y dy, actually means. It's a recipe for telling you how much the value x squared plus y squared changes as determined by the point xy where you start and the tiny step dx dy that you take.
Yeah, I got it.
And as with all things derivative, this is only an approximation, but it's one that gets truer and truer for smaller and smaller choices of dx and dy. The key point here is that when you restrict yourself to steps along the circle, you're essentially saying you want to ensure that this value of s doesn't change. It starts at a value of 25, and you want to keep it at a value of 25. That is, ds should be 0. So setting the expression 2x dx plus 2y dy equal to 0 is the condition under which one of these tiny steps actually stays on the circle.
Yeah.
Again, this is only an approximation. Speaking more precisely, that condition is what keeps you on the tangent line of the circle, not the circle itself. But for tiny enough steps, those are essentially the same thing. Of course, there's nothing special about the expression x squared plus y squared equals 5 squared. It's always nice to think through more examples, so let's consider this expression sine of x times y squared equals x. This corresponds to a whole bunch of U-shaped curves on the plane.
Oh,
And
this
those
was the
curves,
curve.
remember,
That
represent
was
all of the
curve.
points xy where the value of sine of x times y squared happens to equal the value of x. Now imagine taking some tiny step with components dx, dy, and not necessarily one that keeps you on the curve. Taking the derivative of each side of this equation is going to tell us how much the value of that side changes during the step. On the left side, the product rule that we talked through last video tells us that this should be left d right plus right d left. That is, sine of x times the change to y squared, which is 2y times dy, plus y squared times the change to sine of x, which is cosine of x times dx. The right side is simply x, so the size of a change to that value is exactly dx, right? Now setting these two sides equal to each other is a way of saying, whatever your tiny step with coordinates dx and dy is,
Earlier
if
there were
it's
a
going
lot
to
of
keep
visual
us on the
stuff, but
curve,
now
the
there
values of
aren't.
both the left-hand side and the right-hand side must change by the same amount. That's the only way that this top equation can remain true.
Yeah.
From there,
The change was
depending
the
on
same
what
amount.
problem you're trying to solve, you have something to work with algebraically. And maybe the most common goal is to try to figure out what dy divided by dx is. As a final example here, I want to show you how you can actually use this technique of implicit differentiation to figure out new derivative formulas.
This is really cool. Now, I do know what he's going to say now. Let's say, let's say, till now you know the derivative of e to the power x. Uh, what happened to this? How does this come? So mm, there is still a lot of videos. Yeah. Oh, at 3:15 I have to go somewhere, so not really sure if I will be able to finish it or not today itself, because this video is long Taylor series. I think we should be able to do up to over here. But no, these are also long. Maybe we will not be able to. But fine. I wanted to show you something, but the whiteboard isn't working. About how can we find when to show you something, but it isn't working. Yeah. So what should we do at this point? Should I open OneNote? Okay, so let me do it over here. So basically, like how do we find new formulas through that is basically, let's say we want to find derivative of y equals to ln x. Yeah, we can also write this as e to the power y equals to x, and then using implicit differentiation we can say this as e to the power y dy as dx, and now we can say this as dy by dx equals to 1 by e to the power y, and we know e to the power y is just x, so 1 by x. That's why we know that dy by dx, derivative of y with respect to x, is 1 by x. And note that we weren't really able to find the derivative at first, but using implicit differentiation, changing it to other form, we could do it. So this is how this could be helpful. This is one of the ways.
I've mentioned that the derivative of e to the x is itself. But what about the derivative of its
Again, like how could both of us have the same idea? That's interesting.
inverse function, the natural log of x? Well, the graph of the natural log of x can be thought of as an implicit curve. It's all of the points xy on the plane where y happens to equal ln of x. It just happens to be the case that the x's and the y's of this equation aren't as intermingled as they were in our other examples. The slope of this graph, dy divided by dx, should be the derivative of ln of x, right? Well, to find that, first rearrange this equation, y equals ln of x, to be e to the y equals x. This is exactly what the natural log of x means. It's saying e to the what equals x. Since we know the derivative of e to the y, we can take the derivative of both sides here, effectively asking how a tiny step with components dx, dy changes the value of each one of these sides. To ensure that a step stays on the curve, the change to this left side of the equation, which is e to the y times dy, must equal the change to the right side. which in this case is just dx. Rearranging, that means that dy divided by dx, the slope of our graph, equals 1 divided by e to the y. And when we're on the curve, e to the y is, by definition, the same thing as x. So evidently, this slope is 1 divided by x.
Yeah.
And of course,
So we got the result, yeah. In just a second. Just a second. Okay, fine. So we got the derivative, yeah.
an expression for the slope of a graph of a function written in terms of x like this
And also
is the derivative of that
slope
function.
is just 1 by x.
So evidently, the derivative of ln of x is 1 divided by x.
That's pretty a nice derivative for such complex function.
By the way, all of this is a little sneak peek into multivariable calculus,
Yeah.
where you consider functions that have multiple inputs and how they change as you tweak those multiple inputs. The key, as always, is to have a clear image in your head of what tiny nudges are at play and how exactly they depend on each other. Next up, I'm going to be talking about limits.
Oh, so we
and
have
how
already
they're
completed 5 of videos and 5 more are there, yeah. But there are 12 videos, I guess. These 2 are extra, that means.
used to formalize the idea of a derivative.
Okay, so finally we are formalizing it through the first principle definition. Nice. Let's go to next video. Limits, L'Hopital's rule, and epsilon delta definition. Nice. I think this is gonna be interesting because I have heard that he's gonna give the proof of L'Hopital's rule in a symmetric way, which I have just seen a brief glimpse and not the whole picture. I think this was gonna be interesting one. Basically, this one, these two were okay. No, not this one, but 6 was kind of boring for me. Now I think 7 gonna be interesting.
Oh.
Yeah. Calculus required continuity, and continuity was supposed to require the infinitely little, but calculus required continuity, and continuity was supposed to require the infinitely little, but nobody could discover what the infinitely little might be. Nice. And as always, before we begin, I'm gonna go to restroom. Prakash Pant is back again to watch the video of limits, L'Hopital's rule, and epsilon delta definitions. Nice.
The last several videos have been about the idea of a derivative, and before moving on to integrals, I want to take some time to talk about limits. To be honest, the idea of a limit is not really anything new. If you know what the word approach means, you pretty much already know what a limit is. You could say that it's a matter of assigning fancy notation to the intuitive idea of one value that just gets closer to another. But there actually are a few reasons to devote a full video to this topic. For one thing, it's worth showing how the way that I've been describing derivatives so far lines up with the formal definition of a derivative as it's typically presented in most courses and textbooks. I want to give you a little confidence that thinking in terms of dx and df as concrete, non-zero nudges is not just some trick for building intuition. It's actually backed up by the formal definition of a derivative in all of its rigor.
Yeah.
I also want to shed light on what exactly mathematicians mean when they say approach in terms of something called the epsilon delta
That was
definition
epsilon delta definition, yeah. Goal 1 formal definition, and goal 2 epsilon definition in L'Hopital.
of limits. Then we'll finish off with a clever trick for computing limits called
Yeah,
L'Hopital's
I think
rule.
he's gonna give visual proof
So,
as well.
first things first, let's take a look at the formal definition of the derivative.
Okay.
As a reminder, when you have some function f of x, to think about its derivative at a particular input, maybe x equals 2, you start by imagining nudging that input some little dx away, and looking at the resulting change to the output, df. The ratio df divided by dx, which can be nicely thought of as the rise over run slope between the starting point on the graph and the nudged point, is almost what the derivative is. The actual derivative is whatever this ratio approaches as dx approaches 0.
Okay.
And just to spell out a little of what's meant there, that nudge to the output, df, is the difference between f at the starting input plus dx and f at the starting input, the change to the output caused by dx. To express that you want to find what this ratio approaches as dx approaches 0, you write lim for limit, with dx arrow 0 below it. Now, you'll almost never see terms with a lowercase d, like dx, inside a limit expression like this. Instead, the standard is to use a different variable, something like delta x, or commonly h for whatever reason. The way I like to think of it is that terms with this lowercase d in the typical derivative expression have built into them this idea of a limit, the idea that dx is supposed to eventually go to 0.
Nice.
So in a sense, this left-hand side here, df over dx, the ratio we've been thinking about for the past few videos, is just shorthand for what the right-hand side here spells out in more detail, writing out exactly what we mean by df, and writing out this limit process explicitly. And this right-hand side here is the formal definition of a derivative, as you would commonly see it in any calculus textbook.
Yeah.
And if you'll pardon me for a small rant here, I want to emphasize that nothing about this right-hand side references the paradoxical idea of an infinitely small change. The point of limits is to avoid that.
He's ranting. Let
Paradoxical
me
idea
hear
of
it properly.
emphasize that nothing about this right-hand side references the paradoxical idea of an infinitely small change. The point of limits is to avoid that.
Okay, yeah,
This
it does
value
avoid
h
that
is
paradoxical
the
idea.
exact same thing as the dx I've been referencing throughout the series. It's a nudge to the input of f with some non-zero, finitely small size, like 0.001. It's just that we're analyzing what happens for arbitrarily small choices of h. In fact, the only reason that people introduce a new variable name into this formal definition, rather than just, using dx, is to be super extra clear that these changes to the input are just ordinary numbers that have nothing to do with infinitesimals. Because the thing is, there are others who like to interpret this dx as an infinitely small change, whatever that would mean. Or to just say that dx and df are nothing more than symbols that we shouldn't take too seriously. But by now in the series, you know I'm not really a fan of either of those views. I think you can, and should, interpret dx as a concrete, finitely small nudge, just so long as you remember.
You should, I'll support this idea, to take them as small numbers.
To ask what happens when that thing approaches 0. For one thing, and I hope the past few videos have helped convince you of this, that helps to build stronger intuition for where the rules of calculus actually come from.
Yeah,
But it's not just some trick for building.
That's even helpful to get the ideas of where the rules of calculus come from. Yeah, and we have been doing this in all the discussion still now.
Intuitions. Everything I've been saying about derivatives with this concrete finitely small nudge philosophy is just a translation of this formal definition we're staring at right now.
Yeah.
So, long story short, the big fuss about limits is that they let us avoid
That is actually true. This is the closing bracket. That was nice.
talking about infinitely small changes, by instead asking what happens as the size of some small change to our variable approaches 0. And this brings us to goal number 2, understanding exactly what it means for one value to approach another. For example, consider the function 2 plus h cubed minus 2 cubed all divided by h. This happens to be the expression that pops out when you unravel the definition of a derivative of x cubed evaluated at x equals 2, but let's just think of it as any old function with an input h. Its graph is this nice continuous looking parabola, which would make sense because it's a cubic term divided by a linear term. But actually, if you think about what's going on at h equals 0, plugging that in, you would get 0 divided by 0, which is not defined. So really, this graph has a hole at that point, and you have to kind of exaggerate to draw that hole, often with a little empty circle like this. But keep in mind, the function is perfectly well defined for inputs as close to 0 as you want. And wouldn't you agree that as h approaches 0, the corresponding output, the height of this graph, approaches 12? And it doesn't matter which side you come at it from.
Yes.
That limit of this ratio, as h approaches 0, is equal to 12. But imagine that you are a mathematician inventing calculus, and someone skeptically asks you, well, what exactly do you mean by approach? That would be kind of an annoying question. I mean, come on, we all know what it means for one value to get closer to another. But let's start thinking about ways that you might be able to answer that person, completely unambiguously.
Yeah, so he is trying to give the reasons why we are making this absolute delta definition, so that there will be no sort of ambiguity. Yeah, because approach or is kind of ambiguous. It can mean anything. Yeah, according to the interpretation. So he is trying to give the reason why we need this definition. Yeah.
For a given range of inputs within some distance of 0, excluding the forbidden point 0 itself, look at all of the corresponding outputs, all possible heights of the graph above that range. As the range of input values closes in more and more tightly around 0, that range of output values closes in more and more closely around 12. And importantly, the size of that range of output values can be made as small as you want.
Yeah.
As a counterexample,
the output range can be made as small as you want. Still, there will be a size input range. Yeah. Output range is called epsilon and input is delta. Where did we go?
We all know what it means for one value to get closer to another, but let's start thinking about ways that you might be able to answer that person, completely unambiguously. For a given range of inputs within some distance of 0, excluding the forbidden point 0 itself, look at all of the corresponding outputs, all possible heights of the graph above that range. As the range of input values closes in more and more tightly around 0, that range of output values closes in more and more closely around 12. And importantly, the size of that range of output values can be made as small as you want. As a counterexample, consider a function that looks like this, which is also not defined at 0, but it kind of jumps up at that point. When you approach h equals 0...
This is a nice example to understand absolute delta definition, because just from the places where it works, that doesn't give any intuition, but from the places that it doesn't work, it will give you intuition on why this definition makes sense now.
From the right, the function approaches the value 2, but as you come at it from the left, it approaches 1. Since there's not a single clear, unambiguous value that this function approaches as h approaches 0, the limit is simply not defined at that point. One way to think of this is that when you look at any range of inputs around 0 and consider the corresponding range of outputs, as you shrink that input range, the corresponding outputs don't narrow in on any specific value. Instead, those outputs...
Basically, the output range should have also narrowed down, but it should have narrowed down, but It isn't, so that's why it's undefined.
Battle a range that never shrinks smaller than 1, even as you make that input range as tiny as you could imagine. And this perspective of shrinking an input range around the limiting point and seeing whether or not you're restricted in how much that shrinks the output range.
This gives me a completely different perspective other than what I had developed during solving problems. Solving some limit problems using absolute linear definition doesn't really give us the intuition that he gave me now. So this one is so cooler and nicer than what I had really thought of all these days. And that's why he is better. Nice finding.
Leads to something called the epsilon delta definition of limits. Now, I should tell you, you could argue that this is needlessly heavy duty for an introduction to calculus. Like I said, if you know what the word approach means, you already know what a limit means. There's nothing new on the conceptual level here. But this is an interesting glimpse into the field of real analysis, and it gives you a taste for how mathematicians make the intuitive ideas of calculus a little more airtight and rigorous. You've already seen the main idea here. When a limit exists, you can make this output range as small as you want. But when the limit doesn't exist, that output range cannot get smaller than some particular value, no matter how much you shrink the input range around the limiting input. Let's phrase that same idea, but a little more precisely. Maybe in the context of this example where the limiting value was 12.
I think the definition
A little
should
more
be
range
for
around.
any small delta, any small epsilon, however small we might want to make the epsilon, that means the gap between the outputs, there should be some delta. But if we make epsilon really small, there's no delta. So I think that should be the definition.
Around the limiting input. Let's phrase that same idea, but a little more precisely. Maybe in the context of this example where the limiting value was 12. Think about any distance away from 12, where for some reason it's common to use the Greek letter epsilon to denote that distance.
Yeah.
And the intent here is going to be that this distance epsilon is as small as you want. What it means for the limit to exist is that you will always be able to find a range of inputs around our limiting point, some distance delta around 0, so that any input within delta of 0 corresponds to an output within a distance epsilon of 12. And the key point here is that that's true for any epsilon, no matter how small.
That's the key
You'll
point. It should be true for any epsilon.
always be able to find the corresponding delta. In contrast, when a limit does not exist, as in this example here,
Now
you can
won't
find
be
a
able to
sufficiently small epsilon, like 0.4,
Yeah.
so that no matter how small you make your range around 0, no matter how tiny
So this video seems to be interesting, because I got to have some new intuitions.
delta is, the corresponding range of outputs is just always too big. There is no limiting output where everything is within a distance epsilon of that output. So far, this is all pretty theory heavy, don't you think? Limits being used to formally define the derivative, and then epsilons and deltas being used to rigorously define the limit itself.
But
So let's finish things off here with
I
a
really enjoyed this because this was a new intuition for me.
trick for actually computing limits. For instance, let's say for some reason you were studying the function sine of pi times x divided by x squared minus 1. Maybe this was modeling some kind of dampened oscillation. When you plot a bunch of points to graph this, it looks pretty continuous. But there's a problematic value at x equals 1. When you plug that in, sine of pi is, well, 0, and the denominator also comes out to 0. So the function is actually not defined at that input, and the graph should really have a hole there. This also happens, by the way, at x equals negative 1, but let's just focus our attention on a single one of these holes for now. The graph certainly does seem to approach a distinct value at that point, wouldn't you say? So you might ask, how exactly do you find what output this approaches as x approaches 1, since you can't just plug in 1? Well, one way to approximate it would be to plug in a number that's just really close to 1, like 1.00001. Doing that, you'd find that this should be a number around negative 1.57. But is there a way to know precisely what it is? Some systematic process to take an expression like this one, that looks like 0 divided by 0 at some input, and ask what is its limit as x approaches that input? After limits so helpfully let us write the definition for derivatives, derivatives can actually come back here and return the favor to help us evaluate limits. Let me show you what I mean. Here's what the graph of sine of pi times x looks like. And here's what the graph of x squared minus 1 looks like. That's kind of a lot to have up on the screen, but just focus on what's happening around x equals 1. The point here is that sine of pi times x and x squared minus 1 are both 0 at that point. They both cross the x-axis. In the same spirit as plugging in a specific value near 1, like 1.00001, let's zoom in on that point and consider what happens just a tiny nudge dx away from it.
Okay. So both the curves have value at 0. So it's going to try and show me y by x. Okay.
The value sine of pi times x is bumped down, and the value of that nudge, which was caused by the nudge dx to the input, is what we might call d sine of pi x. And from our knowledge of derivatives, using the chain rule, that should be around cosine of pi times x times pi times dx. Since the starting value was x equals 1, we plug in x equals 1 to that expression. In other words, the amount that this sine of pi times x graph changes is roughly proportional to dx, with a proportionality constant equal to cosine of pi times pi. And cosine of pi, if we think back to our trig knowledge, is exactly -1. So we can write this whole thing as negative pi times dx. Similarly, the value of the x squared minus 1 graph changes by some dx squared minus 1. And taking the derivative, the size of that nudge should be 2x times dx. Again, we were starting at x equals 1, so we plug in x equals 1 to that expression, meaning the size of that output nudge is about 2 times 1 times dx. What this means is that for values of x which are just a tiny nudge dx away from 1, the ratio, sine of pi x divided by x squared minus 1, is approximately negative pi times dx divided by 2 times dx.
So how was that equal?
Zoom in on that point and consider what happens just a tiny nudge dx away from it. The value sine of pi times x is bumped down, and the value of that nudge, which was caused by the nudge dx to the input, is what we might call d sine of pi x.
So how did that height was d sine of pi x? Oh, yeah, of course.
And from our graph changes x equals 1, so we
because that was the change in height, yeah. For the change in x, this is the change in height, so that's why that was d sine of dx, and this is d extra minus 1, yeah, fine.
plug in x equals 1 to that expression, meaning the size of that output nudge is about 2 times 1 times dx.
Oh, now they just cancel.
What this means is that for values of x which are just a tiny nudge dx away from 1, the ratio, sine of pi x divided by x squared minus 1, is approximately negative pi times dx divided by 2 times dx. The dx's here cancel out, so what's left is negative pi over 2.
Oh, nice.
And importantly, those approximations get more and more accurate for smaller and smaller choices of dx, right? So this ratio, negative pi over 2, actually tells us the precise limiting value as x approaches 1. And remember, what that means is that the limiting height on our original graph is evidently exactly negative pi over 2. Now, what happened there is a little subtle, so I want to go through it again, but this time a little more generally. Instead of these two specific functions, which are both equal to 0 at x equals 1, think of any two functions, f of x and g of x, which are both 0 at some common value, x equals a. The only constraint is that these have to be functions where you're able to take a derivative of them at x equals a, which means that they each basically look like a line when you zoom in close enough to that value. Now, even though you can't compute f divided by g at this treble point, since both of them equal 0, you can ask about this ratio for values of x really close to a, the limit as x approaches a. And it's helpful to think of those nearby inputs as just a tiny nudge, dx, away from a. The value of f at that nudged point is approximately its derivative, df over dx, evaluated at a times dx. Likewise, the value of g at that nudged point is approximately the derivative of g, evaluated at a, times dx. So near that treble point, the ratio between the outputs of f and g is actually about the same as the derivative of f at a times dx divided by the derivative of g at a.
This was a pretty nice
dx.
proof, yeah.
Those dx's cancel out, so the ratio of f and g near a is about the same as the ratio between their derivatives.
Now, one of the other proofs that I've seen is also like this. What you're going to do is, basically, let's say you have to find, let's say we have to find out limit x tends to a of f of x by g of x. And let us say that f of a is actually 0. Yeah. In that case, you can first subtract f of a from both of them. Also g of a, because g of a is also 0, because this is in 0 by 0 form to use L'Hopital's rule. G of a. Now you can divide this by x minus a. Yeah, because x minus a is not really 0, because x is just approaching to a. Yeah, so x minus a by g of x minus g of a by x minus a. Now you get the proof. This is also easier proof, but this doesn't show us why that should hold true. Yeah, this is not the visual proof though. So the other proof is better, but this is also in proof. Yeah.
Because each of those approximations gets more and more accurate for smaller and smaller nudges, this ratio of derivatives gives the precise value for the limit. This is a really handy trick for computing a lot of limits. Whenever you come across some expression that seems to equal 0 divided by 0 when you plug in some particular input, just try taking the derivative of the top and bottom expressions
And I was hoping
plugging
that he
in.
would also prove it for infinity by infinity form, but he didn't. But let's see he would do it or not.
That same treble input. This clever trick is called L'Hopital's rule. Interestingly, it was actually discovered by Johann Bernoulli, but L'Hopital was this wealthy dude who essentially paid Bernoulli for the rights to some of his mathematical discoveries.
La, I never knew this. That this was by Bernoulli. L'Hopital's paid.
Academia is weird back then, but hey, in a very literal way, it pays to understand these tiny nudges. Now right now, you might be remembering that the definition of a derivative for a given function comes down to computing the limit of a certain fraction that looks like 0 divided by 0. So you might think that L'Hopital's rule could give us a handy way to discover new derivative formulas.
Yeah.
But that would actually be cheating, since presumably you don't know what the derivative of the numerator here
Yes.
is. When it comes to discovering derivative formulas, something that we've been doing a fair amount this series, there is no systematic plug-and-chug method. But that's a good thing. Whenever creativity is needed to solve problems like these, it's a good sign that you're doing something real, something that might give you a powerful tool to solve future problems. And speaking of powerful tools, up next I'm going to be talking about what an integral is, as well as the fundamental theorem of calculus. And this is another example of where limits can be used to help give a clear meaning to a pretty delicate idea that flirts with infinity. As you know, most support for this channel comes through Patreon, and the primary perk for patrons is early access to future series like this one, where the next one is going to be on probability. But for those of you who want a more tangible way to flag that you're part of the community, there is also a small 3 blue 1 brown store. Links on the screen and in the description. I'm still debating whether or not to make a preliminary batch of plushy pie creatures. It kind of depends on how many viewers seem interested in the store more generally. But let me know in comments what other
Okay, so we have like completed lucky 7 videos. Yeah. and there are few more, five more to go. But I do have a class at 3:15, and I know that this video isn't going to be completed in 20 minutes. It will take some time more. So I think this should be the end for today's session of watching and discussing. Basically, initially I made a lot of discussions, but later on, these two videos, like I did not find, like there weren't any questions for us to do something like that. But maybe I wasn't active as well. Yeah, but it was a nice time like discussing this with you guys. And next time, I will see you on integrals, and let us discuss on the integrals together next time. Thanks for watching. Basically, ideal me was there, and one other viewer is also there. Thanks for watching this video, and yeah, I hope you enjoyed my discussion of these things, and yeah, I hope it helps. And thanks for watching.